in the environment. For instance, a last example, and I finish, I think I spoke too much. For instance, when we see a message from a gravitational wave, we try to communicate it to the rest of the world within seconds. So this is a classical thing of early warning that is necessary, more and more necessary, unfortunately, because of climatic change and catastrophes, social things that may happen. So having said all that, thank you again, Minister, for spending this time with us.
Thank you, Stavros, also for your words. Very good. I think this was a wonderful start for our afternoon session. Thank you again, Minister De Pedis. I think this is really encouraging for us. And one aspect that I want to add, which is of course implied in all space missions these days, but of course lunar gravitational wave detection requires international collaboration and cooperation to make it happen. And of course that aspect is something that we are working on directly also with this workshop, which indeed managed to attract scientists from all around the world to participate, which is I think a good sign and shows the interest that we have around the world for this project. So thank you again. And indeed, at this point, I would say that it is time to move on with the science part of our session. And our first speaker will be Francesca Esposito. I don't know, you can first try to share your screen.
Hello?
Yes. So okay. Francesca will tell us about an initiative that she coordinated in Italy to assemble essentially science projects, concepts for a white paper that she presented now to different committees, I would say, but she will tell us more about this. Francesca, it's your stage. Thank you.
Okay, thank you so much. I'll try to share the screen. Do you see my screen?
Yeah, yes, we see it.
Yeah. Okay, thank you so much. So thank you so much for this kind invitation. Today I will talk about this initiative that we carried out in order to aim to write an Italian white paper for the lunar exploration. You know that in these last years, there is a renewed interest in the lunar exploration that is well described in the global exploration roadmap that the most of the space agencies in the world signed in 2018, where they share their common interest to expand the human presence in the deep space in the solar system, having Mars as a ultimate goal and the moon as a necessary intermediate step. So in this big effort, where also the public institution and the private companies are engaged, there are foreseen a lot of space mission, a very large, unprecedented number of space missions that are planned to the moon for the next few years. In particular, there are more than 30 robotic missions that have been already approved and are under development from now up to 2028, and other more than 20 missions have been proposed but are waiting for funds securing. And also there are new actors in this new space race scenario that are new countries such as the South Korea or Turkey, Thailand, Brazil, Israel, South Africa, that testimony the big effort and the big interest that is worldwide about the moon. So considering all these incredible number of opportunities to fly on the moon in the next few years, we tried to start this work in order to focus and to start an Italian roadmap for the moon, taking together the interest, the scientific interest, and also the technologies that can be developed under the Italian leadership in order to achieve these objectives. This first survey collected 36 proposals of instrumentation, and although we cannot say that it is completely exhaustive of Italian interest, we are very satisfied with this very first exercise, because we received a very strong and wide response from all the research institutes in Italy, and also from several universities. The paper also includes a survey of laboratory facilities that are spread in the Italian country that can receive or potentially receive and are interested in study the returned samples from the moon. So we started from the scientific objectives that were agreed and identified by the scientific international community about the moon, that are the same from ESA side and NASA side, and are summarized in this table. So there is a big interest in the science of the moon itself, also to understand the origin of our Earth, but also of the terrestrial planets. There is interest on performing some experiments on the moon, for example, in terms of study the survivability in space, life science, habitability, but also using the moon as a privileged platform to observe the universe. So let's start with the science of the moon. Italian community is very interested in the study of the plasma and dust environment on the moon. You know that dust was revealed since the first Apollo missions, and it is present from the surface up to 100 kilometers above the surface, and created a lot of problems to astronauts for operation and the utilization of instrumentation. So there are several mitigation actions that are studied in this period in preparation to the next human exploration of the moon. We know that the ejection of dust from the surface is due to the impact of fast meteoroids, but also by the electrostatic force that are acting on the lunar surfaces that cause the dust levitation. But also considering that there are different surface potential on the lunar surface that are due to the photoelectron emission in the illuminated side of the surface that charge positively the surface, and the presence of the plasma sheets currents that charge negatively the dark part of the surface, there is a substantial migration of dust between the two areas. So all these phenomena must be understood in order to identify the most effective mitigation of this dust problem. We have to consider that all these characteristics of dust and the plasma environment have been predicted by models, and also have some experimental proof, indirect experimental proof that of this prediction, but was never directly measured. So the international communities asked for a deployment of dedicated instrumentation in order to direct measure the physics of plasma and dust on the moon. For example, on neutral and ion spectrometers, plasma instrumentation, and dust instrumentation. And Italy has a long tradition, for example, in the development of dust instrumentation that have a big heritage, for example, through the Rosetta missions or the ExoMars mission. And so also in this document, there are some of upgraded sensors that will be proposed that also will measure the flux, the size, and the charge, electrical charge of the dust particles. And another idea is to use these instruments over some micro rovers that can work in a logic in a swarm logic in order to perform simultaneous measurements of dust environment from the illuminated part and the dark part of the surface of the moon. This can be easily found, for example, around the terminator or in the lunar polar region, where you can find shadowed regions and illuminated ones. So the idea to get this kind of measurements together in the illuminated and dark region could be a great improvement to understand the dynamic and physics of dust on the moon. Also, to understand the plasma environment, there was proposed some instrument that come from heritage from Baby Colombo Serena instrument that are the energetic neutral atoms detector that will shed light on the interaction between the solar wind and the surface of the moon, and also will help in identify some safer areas for human colonization, for example, around the magnetic anomalies that screen the surface by the from the solar wind. There is also a very big interest in the mapping of polar volatiles. You know that the axis of rotation of the moon has a very small angle, 1.5 degrees, and this causes the topographic depression near the poles to be permanently shaded from the sunlight, and they can reach a very low temperature that allow them to act as traps for volatiles. So it is very important to understand the nature and the abundance of these volatiles around the polar region and all across the moon for different reason. For science, because of course this can shed light on the origin and evolution of water in the inner solar system and also on Earth. And also because it is important for human exploration, for astronauts, but also to produce propellant for next robotic exploration. So there is a big interest in deeply map and quantify and understand the nature of these volatiles, and the international communities identified several instruments that can help for this goal, and are evolved gas analyzer, mass spectrometer, neutron spectrometer, infrared spectrometer, gamma ray spectrometer, ground penetrating radars, and of course the returning on Earth of cryogenically preserved samples captured in interesting areas. The same instrumentation with the additional of some in situ elemental instrument or a regional seismic networks and subsurface sounding can be also useful to shed light and understand deeply the near surface geology of the moon, that is also related to the origin and evolution of terrestrial planets, including the Earth, but is also important in order to properly plan the activity and for example, of extraction of resources from the surfaces, and also the activities of astronauts. And Italy responded for this kind of technology with a huge amount of instruments, because there is a very important heritage in different technologies. For example, radars. We have developed, for example, the radar for the Martian exploration. There is a radar on Mars Reconnaissance Orbiter, the SHARAD, or that was developed in Italy, but also the Marsis radar on the Mars Express missions. But there are several other radars that have been developed also for helping the technological aspect of missions, not only for science. And in the paper, there are 3 different radars that have been proposed: a subsurface sounding radar, and INSAR, and ground penetrating radar. The first 2 to be accommodated in orbiters, and the last one on rover or lander. The idea is try to map with a very high spatial resolution the regions that the subsurface, but also the shell of subsurface, in order to characterize the distribution of volatiles at depths that can be accessible to human explorers. Also, there is a big expertise in Italy about the cameras and the spectrometers. There are lots of such kind of instruments that flown on several missions from Bepi Colombo, ExoMars, Mars Express, Cassini, Rosetta, JUICE, and so on. So there is a very important tradition in Italy for this. And in these years, there is the development of a new generation of this kind of instruments with patented new technologies, for example, for realize a merging between a stereo camera and a spectrometer in a single instrument, from heritage from the Symbiosis instrument on board the Bepi Colombo. Or, for example, there has been developed a novel bifocal panoramic lens that is a lens that is able to acquire in the same time a panoramic image and a higher resolution one in a strict field of view of the same scene. And also spectral imaging spectrometers to be used on the surface on board the rover or landers that will be a valid support for astronauts for a rapid reconnaissance of the surface composition. And also the Fourier spectrometers to be used on in orbits that comes from heritage of ExoMars or Mars Express and so on. Also, there is a big expertise and interest in development of diffractometers or LIBS spectrometers. Diffractometers, for example, was already developed for the old version of the ExoMars mission. And this instrument, for example, can combine the X-ray fluorescence spectroscopy and the X-ray diffraction in order to analyze in the same time both the chemical and mineralogical composition of the surface. It is also in development some experiment for in situ resource utilization. This is an experiment, for example, here in this picture that is in development at the Politecnico of Milan, where that demonstrate our capability to extract water from dry regolith. So this in view of this kind of utilization of resources on the moon. As we discussed a lot this morning, there is also a big interest in the study of interior from core to crust of the moon, the structure of the moon, and it is a clear need of globally distributed seismic and heat flow network, and also of retroreflector network. And also in this case, Italy responded with several instrumentation with an array of seismic sensors. So some are based on well-consolidated technology, but some are also new. For example, this ultra-stable laser interferometry that use optical fiber cables to get very high sensitivity in the measurements. And this is a new technique that has been successfully proven, for example, in the ocean floor on Earth. And so it could be very, very interesting for the use on the moon. And of course, the lunar ranging that will where in Italy we are developing the next generation of this kind of retroreflectors that will be the topic of a talk in this meeting tomorrow. But the moon, we said that can also be used as a platform to perform some experiment, for example, for lunar science. We have the astrobiology community that is interested and has the expertise to develop some miniature experiments that are aimed to the identification and assessment of organic compounds at the part per billion sensitivity from samples that are extracted from the surface of the moon. And there is also interest in develop some disinfection experiment based on the use of ultraviolet radiation in order to get some disinfection of the future lunar habitat modules. This comes from a study that was done inside the institute in Italy during the COVID pandemic. It was done for COVID and can be used also in space for lunar habitats. And also, moon could be considered as a very privileged platform to observe the universe. In particular, the absence of a substantial atmosphere would allow the detection of cosmic ray or primary cosmic rays directly from the surface, while on Earth we have to go with a balloon platform out of the atmosphere in order to see the primary rays. And also the negligible planetary magnetic field will allow no energy cutoff in the observation of this of the cosmic rays. So Italy proposed 3 instruments in order to make this kind of observation on the surface of the moon. 2 of these are based on consolidated technologies, while the third one is a new emerging technology that uses a radio antenna to exploit the cosmic rays through the use of Ascarian effect. The moon is also a place to study fundamental physics, and this is the topic of this workshop, the use, for example, of seismometers to the physics of gravitational wave, but also seismometers can be used to see the strange quark matter that hits or crosses the moon and cause some vibration that can be detected through seismometry. And also a network of next generation retroreflectors can be used not only to study the structure of the internal structure of the moon, but also to test the theory of general relativity. It is also very useful to use the moon to study high energy physics, because also in this case helps the substantial absence of the atmosphere, so that there is no cutoff in the energy range that can be observed from the moon. And so the Italian community that has a large heritage from the Agile and Fermi instruments proposed several, also in this case, several experiments. Some of these can be ready in very short time. Also, the heliophysics can be studied from the moon. In particular, there is a proposal of a coronagraph that can be accommodated on a small nanosat, because if this instrument is placed on this orbiter around the moon, when it is in the night side of the moon, can use the moon to create a natural eclipse. So it is no more need of system for occultating the sun. And this simplified a lot the design of the optical telescope so that it can be accommodated on a small satellite, for example, a nanosat. Radio astronomy is has an excellent possibility to improve a lot on the surface of the moon, because in particular on the far side of the moon that is screened by the radio emission from the Earth. And also the absence, in any case, of the ionosphere, and also from the moon, the study also of the radiation below 10 megahertz. And also in this case, we have two different experiments that have been proposed by the Italian community on the rover or on the orbit around the moon. As a summary, these collected proposals can be divided in three different categories of TRL. In particular, we have a lot of instruments that are more or less ready because they are essentially the same experiments that have flown on a different mission for the exploration of the solar system, for example, and have some spare parts that can be used or have the instrument spare to be used in, for this scope, and so that they can be used for a very fast opportunity in case there is an opportunity in the first 2-3 years. This kind of instrument can be ready to launch. Then there are other instruments that are new, so are upgrade or new technology, but with a strong heritage from instrument developed in other mission that allow, in any case, a fast development in the time frame of 4-6 years. And then there is another class of instruments that are completely novel, and some are potentially breakthrough, can bring to very interesting new science with the proposals that have no space heritage, but a very important heritage in the same context in terrestrial activities. The outcome of all these studies will be published very soon in a few weeks, so you can see the details of all the proposal that Italy have put in place in this paper very soon. Just this is the last slide, step forward in agreement with ASI. ASI is organizing a workshop in order to collect the proposal of Italian community and to place the base of an Italian roadmap for lunar science. This workshop will be held at the end of January next year or at the beginning of February. It will be decided in these days, and the announcement will be published in few days, at least at the beginning of next week. And also there are several interactions with NASA in place in this moment, together with the Italian Space Agency. We presented the white paper in order to find the common interest in lunar exploration, hoping that some opportunity can be in place for Italy in a short time. Thank you so much.
Thank you very much, Francesca. This was great to see. It was a huge list of involvements of Italian scientists in lunar science and exploration. So that was very impressive. Are there any questions by anybody? Oh, yeah. Okay, 1 second.
You mentioned a swarm of little robots. How far is this? Is it an idea? It has started, having an industrial.
I at the moment, there is no funding, so it can be considered more or less an idea, but there is a big international consortium working on this in projecting, and also a breadboard of some relevant parts are in progress. So it is not just an idea, but with some development, waiting for funding, of course.
Thank you.
Other questions? Maybe I have a question. So do you maybe already have some impression how space agencies think about, about planning of lunar science missions? For example, is your impression that this is like, things that can be done in the near future, foreseeable future, or is there also some long-term, would they even consider at the moment supporting missions that are really require time, like, for example, lunar gravitational wave detection, which of course is nothing that we could immediately realize?
Yes, indeed, this is the scope of the roadmap that we are going to build, starting from these inputs from the Italian community. And as told in the last slides, there are some instruments that we have several instruments that can match each kind of opportunity. So we are investigating with NASA if there could be some opportunity for Italy to fly, for example, in some of the trips that are planned for the Artemis program, but also would like to interact with other space agencies. So it depends on the opportunity that will be will be present. So we have instrument for each time frame. So the idea is, in any case, with the roadmap, is to try to also identify the technologies and the scientific themes that are strategic for Italy to develop, and this probably will be funded in time to allow a growth. But at the moment, there is nothing that is in place. That is some movement, some funding that has been requested, some investigation that has been put in place with the other agencies. So we are in the investigating parts. The important thing is that Italy should be ready to respond as soon as an opportunity will come.
Yeah, thank you. Very clear. Okay. Very good. Thank you again, Francesca. I think we will then move on. Thank you very much.
Thank you so much. Thank you.
Very much. Okay, so I think then we are now continuing with our remote presentation by Salvatore on science potential of terrestrial gravitational wave detectors. So, Salvo, I leave the stage to you. Yes, we can see your screen.
Thank you, Jan. And can you also confirm that you can hear me all right?
Yes.
All right, fantastic. I should be sharing the right screen. Okay, fantastic. All right, ready to go then. First of all, let me thank the organizer for the opportunity of speaking today. And I'm sorry I cannot be there in person. Right, so my job is to talk and give an overview of the science potential of terrestrial gravitational wave detectors, especially in a timeline that may be more relevant for this workshop, which is, at least 10, 15 years from now. Right, so I thought that because in the audience we have, of course, all the people that don't think about gravitational waves every day for a living, that I will give some relevant background to compare and contrast with some of the previous talks, for example, by Stefano about LISA. Right, so let me start with the most basic thing here. Of course, I'm talking about ground-based gravitational waves. We already have some of those operating. In particular, the three you are seeing here on the screen have been taking data for the last few years. So these don't look like, for example, the LISA detector you have heard about earlier. Ground-based detectors are typically L-shaped Fabry-Perron microstring interferometers with the kilometer scale arm length. The two LIGOs that you see here, for example, are 4 kilometers length, and Virgo in Italy is 3 kilometers. There are a few others which are about to be online, like Kagra in Japan, and or will be online in a few years, another LIGO in India. All right, so the main point for what I want to say next about ground-based detectors is that their sensitivity and the regions where they're sensitive in frequency domain, it's radically different than what you can do in space, right? So this is shown in this plot here, where I'm representing on the x-axis frequency and on the y-axis the noise, where for today's purposes, lower is better, pretty much. And the various curves represents, in this case, for LIGO, Virgo looks quite similar, the progression of sensitivity over the last few years. And now I don't need to go in detail here. The main point I want to stress is that we are talking of frequencies between, say, 10 hertz and a few kilohertz, as opposed to, micro or milli or decahertz regions that we have heard about earlier and we'll hear about later today. And now that has pretty dramatic consequences on the type of sources you can observe and the type of science you can do. And the main reason it's what something that has been touched upon earlier is that if you think about the gravitational wave emitted by a compact binary, such as those that we have detected up to date, pretty much, which are not the only type of sources we may detect, but they are the ones that for sure we know we will detect. So if you think about those, I think Stefan has mentioned this earlier, the duration and the characteristic frequency at which the two objects will merge depends at the zeroth order on the total mass in an inverse way, such that the heavier the system, the lower the frequency at which it merges, right? So that implies that while, for example, LISA is sensitive to, say, binary black holes at the center of galaxies, or millions and billions of solar masses, in the ground, we are sensitive to much lighter or less massive objects, right? So we are talking of objects of the order of, 1 to a few hundreds of solar masses, right? And so that will affect everything I say later. Another way of representing this is in a rather cartoonish and complicated diagram, which I'm not going to go in detail of, which shows the type of science, goal and measurements you can perform. This is with ground-based detector only, I should say, as a function pretty much of where your detector is good, at high frequency or, in the middle, or a low frequency, which again, for us in the ground means, 10 or 20 hertz. And again, I won't go through this in detail. The point I want to drive is that as you go to lower and lower frequency, and eventually moon detectors and space detector will be even farther on the left of this diagram, so they're not covered here, you will start seeing topics like measuring the eccentricity of the binary, or measuring something called the memory effect of gravity, or look for intermediate mass black hole, is what this IMBH is, that are going to be they're going to be doable and maybe even better with the space detectors, pretty much. So that's why for the rest of my talk, I thought I would focus instead on a selection of science goal, which can better or uniquely be covered here on the ground, pretty much. For example, measurements of and study of neutron stars. That's what this NS stands for example, through their equational state, or the post-merger behavior. I'm going to talk about those later. So I'm not going to cover, of course, all of the science that can be done on the ground. I'm going to focus on things which seems to be unique to the ground. All right, so back to where we are now, before I move to where we will be next. As I said, Advanced LIGO and Virgo have been now collecting data for a few years. There have been 3 observing run, and as of now, they have detected a few tens of compact binaries, mostly binary black hole. I like this plot because it shows the dramatic change of pace that happened between the second and the third observing run. On the x-axis here, you see the observing time in days. These are non-consecutive, of course. And y-axis, the cumulative number of sources. And you can see how between 02 and 03, this is thanks to the implementation of quantum squeezing, mainly the slope has changed pretty dramatically. All right, so right now we have, we have been detecting pretty much in the last science run, one event per week, right? And overall, a few binary neutron stars, a few binary black hole neutron star mergers, and the tens of binary black hole. And if you want to know more, of course, the LIGO Virgo collaboration has a few recent papers online that describe this data set. Now, that's not what I want to talk about. What I want to talk about is, see the glass half empty, because this is great, but if you think about it a bit more, you realize that even after these detectors are online at their design sensitivity, which will happen in a time scale of 2 to 3 years, they will still be limited by their size, pretty much in the size they can do. And in particular, we are still going to be talking about sources which will be in the local universe. And this is shown in this nice plot from one of the recent LIGO Virgo Kagura paper, where on the x-axis you see the redshift of the sources, and on the y-axis you see the merger rate. So many of them merge per unit volume, per unit time. And you can see that with the current data set, we can pin down this number reasonably well in the very local universe. But as we go farther and farther away on the right side of this axis, the uncertainty increases. And of course, there will be even larger, a larger redshift. Now, this, of course, will get a bit better as time goes by and the detectors improve, but still, we're going to be limited in this region of the redshift space. The number of sources will also be rather limited. We're going to be talking even once at design sensitivity of a few hundred sources per year, most of which binary black holes. They will have low, mostly, to moderate signal-to-noise ratio. And the number of EM bright sources, or sources that will also emit light and will be localized well enough that you can find a counterpart with a telescope, so an EM counterpart, I'm describing my acronyms here, will also be rather limited. So if we want to do more, we need to build something else, right? And that's the main topic of my talk, is what we call third generation or 3G detectors, right? There is not a precise definition of what makes a detector 3G. A rough, I guess, ballpark number is that you want something with a sensitivity, which is a factor of 10 better, more or less, in broadband than advanced detectors like LIGO and Virgo. Now, the nice thing about this is that even this factor of 10 buys you a dramatic improvement in the actual science you can do. And you can show, and I'm going to talk about this, that you can detect, for example, binary black hole, a very large redshift, pretty much as far as there are stars in the universe. And some of them will have incredibly high signal-to-noise ratios, and the numbers will be not on the hundreds, but on the hundreds thousands per year. And those detectors target operation for the second half of 2030. Now, it will take still some time and money. My talk is going to be about science, but I should at least have a couple of slides to give an idea of what I'm talking about in terms of design. There are two main proposals that the community has converged toward. One is called the Einstein telescope. And the idea here is that you build something which is triangular shape. The arms will be 10 kilometers instead of the 4 we have today. And the main difference compared to today's detector, beside the geometry, is that it will be underground instead of being over the ground to gain access to the frequency region around 2 to 3 hertz. The design is very mature. There's been a design report published in 2011 and recently updated. And the very good recent news that we heard about is that the Einstein telescope was recently included in the European Strategic Forum for Research Infrastructure. I cannot really pronounce the acronym. My brain doesn't allow me to, roadmap, which means that, you know, they have a much higher chance, and the European Union has recognized this as a project of critical importance and interest for science. Another possible design, it's called Cosmic Explorer. Here, the geometry remains what we are using now, so L-shaped, is just much bigger. Instead of building 4 kilometers arms, you are now thinking about 40 kilometers. This will be on the ground, and here you have, for example, a possible, you know, artist's impression of it. It will be somewhere empty, like in the middle of a desert in Nevada or in Idaho, and it can also, I should say, even though I won't talk about it in detail, it can be optimized just by changing the, you know, some mirrors in a weeks or month time scales to target either high frequency or medium frequency sources. So it can be a bit versatile that way. All right, so if you want to know more about the detector side of things or anything in particular, I should say that there is an entity called the Gravitational Wave International Committee, or WIC, which is a kind of, you know, entity that collects and coordinates the current and next generation gravitational detectors on ground or space or whatever. And because they recognize the interest of the next generation detector on space, on ground, they have formed a committee focusing on this, which has a nice page. And I'm pointing this to you because it also includes dozens of useful documents, including, for example, the updated Einstein Telescope design report and the Cosmic Explorer Horizon study, which I'm going to talk about in a second. And the other thing I want to stress is that a lot of what I will talk about next generation science relies and really requires to have a network of 3G detectors. So we really want to have more than one of these detectors. All right, so I mentioned the Cosmic Explorer Horizon study. I want to say another couple of lines just because I was involved with it, and these are recently developed documents. I want to be sure people are aware of it. This was born of an NSF-funded study, which we call the Horizon study, to explore the design options and scientific potential of ground-based detectors, especially here in the US, where space is not as constrained as in Europe. And so we recently put together a final document, which is a couple of 100 pages, which is very readable by anyone without really a strong background on gravitational wave instrument or science. So if you are interested and don't think about gravitational waves daily, that's a good reading. And I will also refer often to pictures taken or plots from this document as a CEHS. All right, so in that document, even though that's also true for the Einstein Telescope and 3G detectors in general, we identified a few key science goals that can be reached with 3G detectors. They are represented in this rather nice diagram. There are three main areas which we label as black holes and neutron stars throughout cosmic time, dynamic of dense matter and extreme environments, and extreme gravity and fundamental physics. As I mentioned earlier, not all of these things are unique to the ground, so I will not talk about everything. I will talk about things which are unique to ground, in particular black holes through cosmic history and dense matter in neutron stars. Right, so to go there, let me first show you, oops, too fast, what the sensitivity of this ground-based future detector looks like compared to what we have now. This is the same type of plot I've shown before, frequency on the x-axis and the sensitivity on the y-axis, so lower it's better here. So we are still talking of Hertz to kilohertz region, right? And the two future detectors I mentioned, Cosmic Explorer and Einstein Telescope, are the green and purple curve. You can see that we are basically talking overall of a factor of 10 improvement over what, for example, a LIGO Plus, which is an improved version of LIGO, and Virgo also has its own design, which I don't have on this plot, can do, right? So we're talking about a factor of 10 better, and a low frequency even more than a factor of 10 better. I should also mention an Australian concept for a 2.5 maybe generation detector called NEMO that targets high frequency only. All right, so if you ask yourself what type of reach and since this extra sensitivity buys me, that answer can be provided by this plot, where on the x-axis I'm showing, I'm thinking here only about compact binaries, so two binaries orbiting and merging together. On the x-axis, I'm showing the total mass in solar masses. And on the y-axis, I'm showing the maximum redshift at which these objects can be seen. And the three here small thumbnails represent the three representative systems we have already seen with the Advanced LIGO and Virgo, neutron star binary, 3030 solar mass black hole, and 190521, so 150 solar mass black hole, say. Right. So the point I want to drive with this plot is that with Advanced LIGO, even at its design sensitivity, and same for Virgo, which is the blue curve here, we will be limited for neutron star binaries to redshift of the order of 0.1, 0.2, something like that. And for black hole, it's going to be a bit better, of the order of redshift of order of unity. And and maybe for light intermediate mass black hole, redshift of 2-ish, right? And as we go to this next generation detector, cosmic explorer ET, we are really, exploring pretty much the whole universe. We will be able to see neutron stars up to redshift of several, pretty much at or past the peak of the star formation, and black hole binaries a redshift of tens or hundreds, really, depending on the mass, which is farther than where we expect stars to exist in the first place in the universe. So that's the first topic I want to cover today in terms of 3G science, which is really the redshift reach, the extra information that you can gain by being able to access these objects farther away. And this is nicely shown in this plot coming from a paper by Ken, who is a student here. On the x-axis here, I'm showing again the redshift, and on the y-axis, I'm showing the merger rate, so how many black holes merge per unit volume per unit time. The different colors gives you the contribution to the total merger rate coming from different astrophysical channels, among those that have been suggested, like formation in galactic field in orange, formation in a globular cluster or other types of cluster in blue, and formation from black hole coming from population 3 stars in green. This is the first generation of stars. The point that this plot wants to make is that even with 3 Advanced LIGO Virgo detectors at design sensitivity, you can only see binary black hole up to redshift, as I mentioned earlier, of something like 2 at most. And that it's here, that implies that you're going to miss pretty much entirely population 3 born binary black holes, which would merge a much higher redshift mostly. And also the possibility, you will miss the possibility of distinguishing the high redshift behavior and differences between the other population. So that's one of the main things that 3G detectors buy you that you cannot do now, or you cannot do on space, is building the population of stellar mass binary black hole as a function of redshift. And here again, this blue arrow shows and stress that C and DT can see pretty much all the way to here and farther away. I should also say and stress again that we want a network of detectors, because to measure distances and masses at cosmological distances, you need a network. So to give an example of what can be done, if you want, for example, to detect black holes that come from population 3 stars, of course, I could give a whole talk about why this is important in the first place from a scientific point of view, but Jan only gave me 30 minutes and not 30 days, so I won't. And what these plots show you, it's a measurement of the total merger rate in gray with 2 months of data only, right? And using an approach which is totally unmodeled. So here I'm not really relying on any information from numerical simulation or theoretical input about, what this individual population should look like, which is rather uncertain. I'm just asking a much simpler question. Can I use next generation detectors to look for evidence for a peak on the merger rate, a very high redshift, where I would not expect, nearby populations to contribute to? And what this plot is showing you, it's at the top a universe, which we simulated, of course, where such a population does exist. And on the bottom, at the bottom, a universe where this high redshift population does not exist. And the gray bands here are our measurements, 1 sigma and 2 sigma, right? And the point is that even with a couple of months of data only, you can already show that if there is a peak, you can find it. You can show that it's there. And even better, you can even find where that peak is. So you can measure the location in the redshift space, or pretty much the location of this green dashed line, or where the overall merger rate has this high redshift peak. This is shown here on this plot, where it's a bit complicated, so I won't go through it in detail, but the point he wants to make is that you can pinpoint the true location of this merger peak at high redshift, either with an unmodeled approach, which is called GPR here, it stands for Gaussian progress regression, or even with a modeled phenomenological approach that I'm not going to talk about. So the point is that, again, to summarize, even if you don't have any good model, you can already find this peak and tell that it happens at redshift of 10 or 11 or something like that. All right. But because I told you that with 3G detectors, we can go even farther than redshift of 10 or 15, you can be, or we can be even more ambitious and go after the mergers of so-called primordial black holes, or PBHs. So these are black holes that may not be born from stars after they run out of nuclear fuel, but directly from fluctuations shortly after the Big Bang. And so those would be black holes whose merger rate peaks at even higher redshift than population 3 star, as shown here in this plot, where now the primordial black hole merger is this red curve. So again, it peaks a much higher redshift. And now if you want to make the case that you are detecting a population of primordial black holes, which of course would have dramatic consequences on our understanding of, for example, inflation, you may use a few criteria. You may try to rely on the mass and spin spectrum of primordial black hole or their eccentricity spectrum. However, all of these are rather uncertain. So at least to me, that's my personal opinion, using and relying on the fact that primordial black hole merger should happen at extremely, sorry for the typo here, redshift, it's the safest thing. So the question is, can I measure the merger rate of these objects at such high redshift and make a case that there is another peak at redshift of 30 or 40? And you can play the same game I played before and use even an unmodeled approach, as shown in this cartoon, in this plot here of something we are working on, and show that indeed, if you do have a population of primordial black hole mergers at Z of 30 or 40, even with a few months of data, this is now 7 months of data of 2 Cosmic Explorer and 1 Einstein telescope, you can show that this population exists on the left plot, or puts lower limit, or upper limit, I should say, sorry, in case where it does not exist, as shown on the plot on the right. All right, Jan, I forgot to start my timer, and I always start a bit late. Can you remind me how long I have at this stage?
I would say another 3-4 minutes would be okay.
Okay, then I'm going to accelerate. I was hoping a bit more, but that's fine. One thing I would just mention, because I hope and I assume that Alberto talking after me will cover a bit more, is the opportunity that ground-based 3G detectors will work together with LISA and other possibly decahertz detectors in so-called multi-banding configuration. This is an idea that Alberto, first proposed after the first detection of gravitational waves, and then there have been a lot of follow-up work since. That's the idea that LISA can see stellar mass black holes a few years before they eventually merge in the band of ground-based detector. And that provides a lot of complementary information, especially for heavy or intermediate mass black hole. I assume that Alberto will talk about this later, so I'm going to spend the last couple of minutes on my presentation to say something about neutron star physics. So the point here is that, and this is really something which I think is unique to the ground, because that's physics and gravitational wave physics that happens at the kilohertz region. And the idea is that neutron stars, of course, and matter neutron stars experience the most extreme condition in the visible universe, of course. And that implies that we can exploit neutron stars to explore regions of the phase diagram shown in this cartoon here. Sorry for the lack of tick marks. I'm happy to put numbers vocally if people want, which are not accessible here at Earth. So pretty much high density and high temperature, or low to high temperature, MEVs to tens of MEVs pretty much. And that allows us, among other things, for example, to determine the internal structure of neutron stars, whether they're made of neutrons all the way through, or quarks, or their equational state, and anything in between. As I mentioned, however, if you think about the gravitational wave signal, this information is encoded in the very last few cycles of the spiral, or in the post-in-spiral, so in the post-merger after the two neutron stars have collided. This is kilohertz region. So this is science which is very hard to do now. Of course, advanced detectors have started to say something about the equational state, putting mostly upper limits so far, and shown that is rather compact, the neutron star that we produce. Even as LIGO and Virgo gets better, mostly the information that we will gather will come from the spiral phase. If we're very lucky, we may get hints of post-merger physics, but it's really only with 3G detectors that we'll be able to pretty easily, I would say, measure the equational state from both the spiral and the post-spiral phase. This is shown in these plots here, where I have frequency on the x-axis, and now look, please pay attention. Now we are on the kilohertz region. I don't start from 10 hertz anymore. And on the y-axis, again, the sensitivity. What these various curves in color show are characteristic peaks of gravitational wave emission, which was exact frequency depends on the equational state. So this is peaks after the two neutron stars have merged. And here you see as a representative set of curves, the sensitivity of advanced LIGO and the Einstein telescope. And the point this makes is that with 3G detectors, these features will be visible. This is also stressed in this plot at the bottom, which shows the number of sources every year for which the signal to noise ratio in these features only, so not the overall signal to noise ratio, the post-merger one will be larger than 5. And the point is that as you go from current detectors to next generation, we are talking of order of unity or order of tens of these per year. All right, the very last thing before Jan cuts the microphone, it's multi-messenger astrophysics. We have started, of course, pretty spectacularly doing this now with 17817. I don't need to talk about this very much because I assume everyone knows about it. We detected signals on DM at all bands, from radio to X-ray, and of course that has allowed already to say something about the progenitors of short gamma ray burst, some hints of or improving understanding of kilonova physics, and arc process heavy metal production, and do some cosmology. Now, this was great, and it will get a bit better, but of course it will be fantastic with a network of 3G detectors, because with 3G detectors, we are now talking of hundreds of neutron stars per year, hundreds very well characterized. The total number will be, of course, thousands or millions, right? But hundreds of those every year will have very high signal to noise ratio and very small uncertainty in the sky, as shown in this plot here, which I won't discuss for reason of time. So the point I want to make here is that we will have hundreds of sources, of neutron star sources, for which the source can be pinpointed on the sky with exquisite accuracy even before the signal merge in the gravitational waves spectrum. So allowing for pre-merger pretty much alerts and pointing your telescope even in advance, right? And because we'll have hundreds of sources well characterized per year, that means we're going to cover the parameter space of, for example, the neutron star masses much more than we can do now, and understand much better how the system's parameters, like the masses, for example, again, or spins, affect the type and the energetics of DM emissions we get out of these systems. All right. I think I'm pretty much done. So I will leave my conclusion up on the slide and just stress that there are ample opportunities to get involved with science, with ground-based pretty much 3G science. You can pin me or anyone else in the audience really if you want to know more. People from different communities are of course more than welcome to join, and know what's happening. All right, thank you. I'll stop here. Thank you for listening.
Thank you very much, Salvo, for this great summary of gravitational wave science with terrestrial detectors. Alberto has a question.
Yeah, hi, Salvo. A great presentation. When you showed the constraints that you can put on primordial black holes with the 3G detectors, I mean, you assume that those primordial black holes have stellar masses, right? Because obviously, I mean, that's an assumption that, well, you can make, but it's not obvious, right? They can be in any mass range.
Absolutely. Right. So who was asking the question? I didn't recognize the voice.
I'm here. I'm Alberto Salvatore.
Okay, you're there. Okay, sorry. It's complicated when you're sharing the screen to know who is who. Okay, no, Alberto, yeah, absolutely. That's a fair and totally true point. So that was the kind of, in my mind, conveyed with what I said here, right? So, of course, the heavier the mass, the more the overlap with what one can do in the a lower frequency, so in the deca or milli or microhertz region. And so I did indeed focus on my presentation, at least in my mind, to stellar mass object. So what you say is perfectly correct. Here I'm making the assumption that PBHs will or have, the ones I've used here, a mass spectrum which is of stellar mass, so a few to a few tens stellar masses. And if that is not the case, of course, the heavier I make my primordial black hole, the least, the smallest the number of them I can reach, and it can of course be zero. This is captured by this plot here, where it is shown that if I increase the mass, above a few tens, and also put my sources at redshift, of 30 or 40, of course, at some point I'll start being unable to see them just because of the redshift boost of their mass. Yeah, sorry, Alberto, I should have stressed this again on the slide. That's an assumption that went into this.
Okay, thanks for the clarification.
Yeah.
I have maybe a naive question for the terrestrial gravitation. Okay, for the terrestrial detector, do you have an idea or a strategy to use a very dense seismic network to monitor and model so well the seismic noise that you can efficiently remove part of it?
So I think actually Jan is probably the best question, since Jan is one of the world experts of of low frequency noise. What I can say, working on the instruments, is of course we do all that can be done to remove noise now and in plans for next generation. Of course, eventually you are limited by things like Newtonian noise, which is can be at least partially addressed and canceled, but to some extent. So eventually you are limited by the fact that you are on the ground or a bit better underground. So we have active and passive system to keep the masses isolated from ground motion. But it's not perfect, and that's what gives I probably show this one. That's what explains why the sensitivity on the ground pretty much blows up once you reach 10 hertz today and maybe a few hertz in the future. Jan, I'm sure you can add way more, so I'll shut up and let the expert talk.
Oh, this was very good. Maybe the one thing that I can add is something that also Stefano mentioned in his presentation. There was a kind of noise that they expected at low frequencies, which in the end they were able to reduce because they were not, they didn't have to push so hard to keep everything aligned. So this is a kind of controls noise which you can get, in which you have in these spectra as well, like in LIGO spectra at low frequencies. So to keep everything aligned and operative at high sensitivity, of course, the control itself introduces noise, which is one of the main things we are currently after in the detectors. So also maybe Karan, last question. No, there's actually also, okay. Okay, Marika instead, change of plans.
Salvo, the plot that you show for the sky localization, I imagine that is for 3G detector, is it correct? When you say that there are a lot of sources
Yeah,
with the
so
sky.
sorry, Marika, there's some delay, so I interrupted you. Apologies. But I think I got the question. So this one, it depends. So this shows multiple network configuration. The number I mentioned, hundreds, is for the best network we have considered in this situation, which so is a network indeed. If, of course, you're right, if you decrease the number of detectors, in this plot, I think for whatever reason, we do not have ET only, which would be better, of course, than one L-shaped detector only. Here we only have Cs. Of course, the number decreases dramatically, right, to order of a few tens per year. But this is something that is considered in this plot. So this pretty much gives you the range from the worst case scenario where you only have, that will be this line here, a single L-shape 20 kilometers, that's what this number means, detector, all the way up here to where you have, 240 kilometers detector. And of course, if you add ET, which I may also have in a backup slide, these numbers go even a bit higher. So yeah, this type of science does rely pretty significantly on the idea of having a network of detectors working together.
Yeah, no, because this is an important point for the astronomer, because, okay, you have something that is less than 1 square degree, means some instruments, and if you go with with sky localization with tens of square degree, you need really wide field of view. So I think that is important that we say to the astronomer that in reality, this is the best situation. So 3 interferometers, but that in future, for sure, we will have also situation at the beginning, at least, in which the sky localization will be much larger. And so large field of view are still needed in the future.
Absolutely. Thank you for clarifying that, Mike. I should say that I had to skip, of course, a few things for reason of time. So this plot comes from this Horizon study that I mentioned for C specifically. Of course, I should say, and I did say earlier, that ET has its own document, which is extremely thorough. And of course, there is also a lot of individual people work, including Marika. In our case for CE, because of course with our maybe geometry and design is a bit more in flux than the Einstein telescope, which has been around for more years in terms of concept, we are still considering what kind of science one can do with what type of detector network. So if people are interested in this Horizon study, we actually, including for MMA, for multi-messenger astronomy, we do consider various trade-offs and see what gets better and what gets worse, as represented by this color, depending on whether you have a single detector, a network, how long the arms are, and so on and so forth. So of course, Marika is right. Things depend a lot on the network you are considering, including the fraction of which events are localized better to X many square degrees. So there is a lot of information that people can find here if they want to know more, or in the Einstein Telescope Design Report, which again, if people are interested, it's available in the WIC page.
Okay, thank you. I know that there are other questions, but I want to stop here. I didn't have lunch, but I do want to have dinner. So thank you again, Salvo, for this presentation. And we can continue with Alberto. Does it work? Something seems to happen. Yeah. Is that you? Oh, it's not you. Lui condivide su Zoom. Puoi rimettere Zoom? No, perché lui... No. Ho detto io. Alla fine è uguale? Ma ok. Ale.
Okay, cool. All right, I thank Vitale and Vitale for building so much hype for my talk. So now I feel a little bit, on the spot. As Vitale and as Vitale. Okay, so let me try to be sharp with time since we're already running late. I don't want to interfere with dinner plans or, well, coffee break times even. So I will give a brief overview of LISA science, and I will try actually also to put this a little bit in context with what we're doing here, which is like talking about detecting gravitational waves on the moon. So LISA is is an instrument with a broad range of sources and a broad scientific case. I will concentrate mostly on astrophysical sources, although LISA is also very important in terms of cosmological backgrounds, detecting sources of gravitational wave from inflation, phase transition, and so on and so forth. But since I don't know anything about this, I will focus on the astrophysics part of the LISA science case. So, well, you know pretty much everything about LISA after Stefano's presentation. The only thing that I want to show here is actually the sensitivity curve of the detector and the wide number of sources and wide type of sources that we're going to see at that frequency range, because the milliards frequency range is anticipated to be the range where the largest variety of sources, and not only in numbers, but also, well, maybe not in numbers, but certainly in type. Okay, and in fact, well, LISA is a very is a large enterprise, and there is now a consortium, a scientific consortium that is built around the mission, which counts more than 1,300 scientists. And if you want to join, if you haven't done yet, you find all the information on our website. So going back to the sources, in the milliards frequency regime, you can essentially see gravitational waves on a wide variety of mass scales. So you can see things that are from stellar mass and maybe even substellar mass, what we see from the ground, but also things that are supermassive, okay? And in fact, and as Stefano said this morning, the lower the mass, the higher the mass, the lower the frequency of emission. So with LISA, you can sort of see the early life of low mass binaries and the end point of the life of massive binaries. And because of this, you have a variety of types of sources. And in fact, massive sources involving massive black hole binaries, compact objects orbiting massive black holes, they are evolving in the LISA band. They will in spiral and merge in the LISA band, whereas a stellar mass object will be persistent sources in the LISA band. So you will see like white dwarf binaries from the galaxy, and they will last for the whole mission duration. So you have these two types of sources and two types of signal all together in your detector. And one of the main challenges is to actually be able to recognize all the signal and disentangle them, which is a problem that we have like for 14, 15 years to solve. So let me talk a little bit about those astrophysical sources. And let me start from massive black hole binaries. Okay, massive black hole binaries are the primary targets of LISA. They are super important for the evolution of galaxies and structure. And essentially they form following mergers of galaxies, right? Because we know today that the evolution of galaxies proceed in hierarchical fashion. So big galaxies today are built from a sequence of mergers of smaller galaxies to build ever bigger structures. And we measure at the center of these galaxies massive black holes. Okay, there is one in our Milky Way, there is one in M87, there is one pretty much in every galaxy where we have the resolution and sensitivity to look at the center. Okay, So the obvious thing is that if two galaxies have massive black hole in their center and they merge, the two massive black hole will be dragged to the center because of dynamical friction, and they will form a binary. Okay. Now, how that binary evolves is a bit uncertain because dynamical friction ceases to be efficient when the two massive black holes come together in a Keplerian binary. But then you can interact with a very dense environment of gas and stars, and those could provide physical mechanism to take away the energy and the angular momentum for from the binary, leading to the final gravitational wave emission stage. Okay, so this is a very active field of research involving astrophysicists and gravitational wave physicists. And we are pretty confident that there are several paths, either interacting with star, with gas, or forming triplets of these massive black hole binaries, along which these systems can merge. Okay. And the good thing is that LISA is as any gravitational wave detector, is omnidirectional, and it has a sensitivity which is good enough to see these systems pretty much everywhere in the universe. And in fact, with LISA, you can see mergers of black hole binaries, massive black hole binaries, from few thousand to tens of millions of solar masses anywhere in the universe, up to redshift 20 and beyond. Okay, so if they are there, we will see them. And what I show in this plot is a contour. So this is the log mass redshift plane. Contours are signal to noise ratio contours for binaries at this mass, at this redshift. And the tracks are essentially semi-analytic tracks for evolution of massive black holes from a semi-analytic model. So you see a typical Milky Way-like supermassive black hole at redshift 0, your favorite quasar at redshift 2, or the highest redshift quasar here at redshift 6. And each point here is a merger that happened along the cosmic history of those systems. So the bottom line is that it doesn't matter what type of massive black hole you are considering. They all cut through the LISA band along their cosmic history. And the vast majority of the mergers that they had, we will see them, okay? However, the universe is billions of years old, right? And LISA only works for a few years, right? So it is true that in principle, we could see all the mergers in the universe, but we will see only the mergers that happen, right, in the time frame of our detector. And since galaxies are, 10, 100 billion, okay, and they experience one or few mergers each in their lifetime, you can make math. And it's not hard to find out that you will see tens to hundreds of these mergers with LISA. So we're not talking about millions of sources like 3G detectors, because these systems are inherently much rarer. So depending on properties of this population, which are unknown, because we don't know how this seed forms, we don't know how they evolve in their early phases, okay? So this is pretty much, uncharted territory. You might end up with system with a merger rate for this object, which is few in a year in a LISA mission lifetime, up to several hundreds. But in general, so LISA will provide you like hundreds of detections, and for all this system, you will be measuring the sky localization, the distance, the spins of the black holes, and the system has so high SNR in the final merger and ring down that the spins might be measured with % accuracy, so which is really astonishing, and so on and so forth. So you will, with this population of black holes, you will be able to track the cosmic history of those objects. And there's many things that I can say, but the only thing that I want to show is an early experiment that we tried a few years ago. So this messy plot that doesn't really read. So here, what we did, we played the game of putting together competing models for the evolution of massive black holes. We created data sets, and we gave these data sets to LISA, to a simulator. We simulated the detection, and we asked a friend, okay, you detect this system, which is the parent model, okay? And so essentially those plots here show you the percentage of time, well, the fraction of time the guy was able to distinguish two models with a given confidence. And if you look at them by like this, they're not great, right? You can distinguish between these two models, which doesn't matter what they mean, what it means, but like with I don't know, 95% accuracy only 30% of the time. So that's not great. But in order to make plots that were legible, okay, that were readable, sorry, we had to assume 3 months of observation. So here you have like 5 detections. Okay, if I make this for a 4-year, 5-year detection, all those curves collapse to the corner. Okay, you can figure out whether your seeds were massive or light, or from POP3 or from direct collapse, and so on and so forth. Of course, this is a bit cheating because we assume that the universe is black or white. Okay, we tried also mixing models, and we were able to recover the mixing fraction, and so on and so forth. But it's a nice proof of concept study that you can really disentangle and understand the formation of these massive black holes with LISA. Obviously, this was also said already by Luigi, so I won't spend much time on this. Those massive black holes might and are expected actually to emit electromagnetic radiation because they sit in a dense environment of a galaxy merger, and especially at high redshift, a lot of cold gas is expected to be driven to the center together with the merger in the merger process. So those systems might be active as quasar or as periodic sources anyway. And of course, if you have an emission of electromagnetic radiation, you can go after this emission. And the cool thing, and what this plot shows is the typical sky localization for a relatively low mass and low redshift system that you can achieve with LISA as a function of time to merger. So you see that, so this is the sky localization in square degree, and already a month before coalescence, you already have a better than 10 square degree localization, which is, it happens to be the field of view of LSST. Okay, so for example, you can monitor that region of the sky for a month before merger to see whether you see any periodicity, which is commensurable to what you're measuring in the gravitational wave. Okay, because with LISA, you will measure the frequency and the frequency derivative of the source very easily. And of course, at merger, you might have a localization which is of the order of arc minutes. And this obviously is a strong case to follow up these systems with deep observatories, like, for example, Athena. Okay, and in fact, if you assume that after merger, those systems are going to emit like in a quasar-like fashion, and you consider the Athena sensitivity, what you're really interested in this plot here is the black curve, this solid black curve here, which is essentially the overlap region of LISA and Athena. And you see that, a putative counterpart, quasar-like counterpart for a black hole of a mass of 10 to the 6 to a few 10 to the 7 solar masses is detectable by Athena up to redshift 3. Okay, so in principle, this is a very strong, case for having a certain overlap between the two missions. Because of course, if you can detect and pinpoint the electromagnetic signature of binary merger, there is a number of scientific questions that you can try answer related to interaction between matter and gravity in the strong field regime. You can witness the birth of a quasar, for example, the launch of a jet, but also you can use those things as standard sirens, as we did for GW17 or 817, but at much higher redshift. Okay, so there is a whole number of interesting scientific cases that lie under those, behind those multi-messenger sources. Moving to weaker sources, but definitely super interesting. Another anticipated source for LISA is the spiral of a compact object onto a massive black hole, because these massive black holes in the center of galaxies are surrounded by stars and compact objects. Compact objects especially cluster, segregate to the center. So the actual capture of one of those compact objects by the central massive black hole is not expected to be infrequent. So it's going to happen quite frequently. Those are sources that live for months or years in the LISA band. They perform a number of thousands of cycles in the LISA band, and you can measure the parameters of the central black hole with a ridiculous accuracy. And when I say ridiculous, I really mean ridiculous. So here, so those are, let's say, sort of asymmetric violin plots of the measurement of two interesting quantities of the central black hole. This is the spin magnitude, And you see the order of magnitude of the measurement. It's a part in 10 to the 4 or part in 10 to the 5, okay? So really you measure the spin. And this is the deviation from the Kerr quadrupole moment, okay? So any deviation from Kerr to 10 to the minus 3, 10 to the minus 4 is gonna be measurable. So those are fantastic systems to perform tests of general relativity. So how many such systems do we expect? That's not easy to predict because there is a huge number of uncertainties. So first of all, those are systems that happen around massive black hole of 1 million solar mass or less, of which we don't quite know the mass function. So really, we don't know how many such massive black holes lie at the center of galaxies. Moreover, the rate, given a black hole, the rate of emeries depends really on the environment, which is very uncertain. So overall, we might have like 3 orders of magnitude uncertainty in the rate. So we did some calculation, and what comes out to be conveniently as a lower limit of 1 per year. We just tuned the model to get there. No, well, really, this is as low as we could go. But you might expect up to several thousand such emeries per year, in which case those emeries will produce a stochastic background, which might even be dominant compared to the one that is produced by white dwarf binaries at high frequency. So those emeries are going to be also localized in the sky very well. And again, you can play the usual game to measure Hubble constant and cosmological parameters, but in this case without a counterpart, just through statistical methods, okay? And this is from a paper that came out recently, which shows this proof of concept, and you can see that you can measure the Hubble constant to 1.5% level. Okay, moving down in mass, let's talk a little bit about galactic binaries. So those are guaranteed sources, and the sources plot that you see in those plots are what we call verification binaries. These are binaries that are detected electromagnetically. We know they are binary. We can measure their period. We know roughly their distance. And so we know what is their gravitational wave signal. So when we switch on LISA, we're going to see these systems, and those are sources that help us calibrating the instrument. What we see in electromagnetic is just the tip of the iceberg, literally, because what you expect is that, what we know is that in the galaxy, there are tens of millions such binaries. And those binaries will form a foreground, an astrophysical foreground. I forgot to kill my email. And the brightest of those sources, you will be able to subtract, and we are talking about tens of thousands of sources. But the rest will produce this stochastic foreground that we were talking about before and that you see here, okay? So this is just the irreducible foreground that adds to your instrument noise. And what I was saying before about emeries is that if you have too many extreme acceleration spirals, they will produce a stochastic foreground that extends here at higher frequency, okay? So those foregrounds are great because they are signals that carry information, but they're also a problem because, of course, they reduce the sensitivity of your detector to other sources. And of course, since the detection of GW 150914, we realized that heavy stellar mass black holes will be observed by LISA. And moreover, some of them can be observable both in the LISA band and in the LIGO band, because, for example, GW 150914, which is the black curve here, like 5 years before merger, was emitting at this frequency here, around 0.01 hertz, right in the middle of the LISA sensitivity. So in principle, there is a number of sources that can be seen from space and from the ground. How many of them? Well, that's uncertain, and it really depends mostly on the details of the high frequency sensitivity of LISA, because with advanced LIGO and Virgo, and especially with 3G detectors, we will see stellar mass black holes of 50, 100 solar masses up to high redshift. But LISA is not built for this type of sources. So really, you can see them only if your high frequency sensitivity is good enough, okay? And the forecast at the moment, what we think we can do is to detect perhaps up to 100 or a few hundred such binaries. And of these few hundreds, perhaps few tens are going to be multi-band sources going from the LISA to the LIGO band. And of course, those are sources that are very interesting for a number of reasons. It's very dark. For a number of reasons. First of all, because you can do multi-band astronomy, you can issue alerts, because LISA will tell you for those systems, LISA will tell you few weeks before merger with sub-degree precision where the signal, the binary is going to merge, okay? And it will tell you within less than a minute precision when it's going to merge, okay? Of course, those are black hole binaries, so the vanilla scenario, in the vanilla scenario, you don't expect really a counterpart, but of course, if you know exactly where and when they're merging, you can, instead of relying on some wild field instrument to see them, to be, you know, pointing there when they happen, you can point really your best instrument at that location and do deep surveys, okay? Right, so this gives me the, how much time do I have? 10, okay, but 10 minutes. Okay. So this, of course, gives me the possibility to talk a little bit about multi-band and to frame all of this in the context of a lunar observatory. In fact, so those are slides that really were prepared for 3G detectors. So if I show you the same plot as before, or with mass on the x-axis and redshift on the y-axis, and I put LISA and now, for example, ET, right? You see that here there is this triangle shape at the bottom where the two sensitivity overlap, okay? And this is the realm of what we call multi-band astronomy, which you can do for stellar origin black holes, for example, but obviously the main sources for this are intermediate mass black holes. And Karen had a very nice paper about this a couple of years ago or last year. Now, an interesting question would be, I don't know if some calculation has been done already, where a lunar observatory will place in a plot like this, because if it has a sensitivity that is in between LISA and 3G, it might really extend at higher redshift this overlap region, okay? And I will show you that this is important for a number of reasons. So we know that black holes cover a range, a wide spectral range from the stellar mass objects here that we detected with LIGO Virgo to the supermassive black holes that we hope we will detect with LISA and also with pulsar timing. Very nice experiment that I don't have time to talk about, but you can check it out if you're interested. Now, remember, more massive, lower frequency, right? So if I take these to be the frequency space and strain amplitude of the wave, you see where LISA and LIGO more or less are, and pulsar timing at the very high end. And you can take this plot and flip it, right? And you see that the intermediate mass region, which is the green band there, lies in between LISA and LIGO, okay? And here I added a tentative sensitivity curve for this lunar observatory, which was kindly provided by Jan yesterday night. And you see that really falls in between the ground-based and the space-based detectors, right? So here one could add also, for example, third generation detectors. We're going to be somewhere, here a little bit at lower frequency. So this opens, of course, an interesting space of synergies between those detectors because, right, we know that LISA is great to detect massive black holes, but we also know that it cannot really detect things below 1,000 solar masses at high redshift, okay? So really, what this plot here shows is the, let's say, density of mergers of black holes, okay, in a model where these massive black holes come from POP3, population 3 remnants, so low mass, high redshift binaries. And those are the usual LISA contours. And you see that really LISA cannot see this region here, okay? So if these massive black holes come from POP3, we won't see, let's say, the first merger, their first growth with LISA. However, if we have, for example, LISA and ET, right, we might be able to see like the seeds with ET and then their grown-up counterparts with LISA. But still, you see there is this gap in the middle, right? And if a lunar telescope kicks in, right, it might be very efficient in filling this gap and really give us the overall picture of how these systems evolve. Because, you know, you can see stellar mass black hole with ET at high redshift, but it's not going to be easy to prove that those black holes are actually the seeds of the supermassive black holes that we see in the LISA band, because those might just well be high redshift POP3 black holes that never grow to massive black hole. Okay, so having something in between, right, is going to be very important to build a consistent story for the growth, history growth of these systems. And obviously, well, if you go to multi-band sources, you see really that a lunar experiment really places itself between LISA and the ground-based. And so according to this plot, the sensitivity should be actually quite a bit better than LISA for those sources. So really, you will have many more multi-band sources to follow way before merger with your into your ET band, let's say, or Cosmic Explorer. And a thing that might be interesting, even though, you know, as Salvatore said before, I should say Salvo, as Salvo said before, ET and 3G detectors will have the capability to provide alert for neutron star binaries, for some of them at least. But certainly with the lunar observatory, you will be able actually to do to give very early warnings to ground-based detectors, even for neutron star binaries. Because the problem with LISA is not that you cannot see neutron star binaries with LISA. You can in the galaxy, for example, but you see them way before merger, okay? Whereas around the Earth, or 1 Earth or point something Hertz, you are right in the place where neutron star binaries take months or years to merge. So really, you can see them in the, you know, with your detector on the moon, and then tell your friends on, you know, LIGO, Virgo, 3G, whatever is going to be on the ground, when and where those binary neutron stars are going to merge. Okay, which will allow you to go very deep and maybe to see also, you know, gamma ray bursts that are very much off axis. You might see like kilonovas that are not associated with AJRB and so on and so forth. So I think this is a very interesting connection that put together LISA, a lunar detector, and third generation ground-based detectors. Okay, so I just leave you with this slide, which shows the variety of sources that populate the binary gravitational wave landscape, and, you know, the place where a lunar observatory is. That's going to be very interesting. So you see, this is a 10 to the 4 solar mass black hole binary, and the merger actually happens outside LISA, but inside the band of this detector. And a 10 to the 3 solar mass black hole will also be inside the detector. But you can see, you know, the spiral of a lot of compact objects, and in particular, you can give alerts for ground-based detector for the merger of neutron star binaries. And yeah, with that, I'm done, and I hope I was on time.
Thank you, Alberto. Wonderful talk. Stefano.
It's a question to these guys, not to you.
Ah, okay.
Given that plot that shows the importance of covering the gap between ground-based and, if you would focus just on that band, would you change your detector? Would it make your life easier?
That's what we're doing, and let me make the publicity that soon you will see all the horizons in between, plus the times, plus all that. We did this homework exactly.
Mm-hmm.
If you cover just that, which is exactly from 1 Hertz to a millihertz, you'll see our horizon. You'll see how it exactly covers this. You have 3 3 mountains: the mountain of ET, the mountain of LISA, and in the middle, the mountain of horizon mountain of the
which we're going to see now, I presume.
So, I mean, to comment on that, I mean, there are two different approaches. So, you know, doing something like LIGO or Cosmic Explorer on the moon, of course, opens up the full window because you wouldn't have to worry about the seismic background. But unfortunately, it turns out that the decihertz band is exactly where you expect to be limited by the seismic background on the moon. So you can make your detector better and better. It doesn't gain you any sensitivity unless you come with a strategy to reduce that background in your data.
Okay.
Of course, these are problems we already have in LIGO Virgo as well. So we have our technologies for that. But to do something on this, like this on the moon, as we want to do here. Sorry. Will be very challenging. So we shouldn't hope for huge steps forward in that band beyond that level. But, you know, anyway, it's something that we have to look at very carefully. Yes.
It was a very nice talk, which was covering many topics. So I'll ask about one. You mentioned this association of merging black holes measured by LISA with quasars. I don't understand it. The typical quasars have masses of 10 to the 8 solar masses. I don't think we know of any quasar with 10 to the 6 solar mass. So why do you think that the merger of two 10 to the 6 solar masses will produce suddenly a quasar? Is there any physical motivation or observational motivation for this idea?
Yeah, I might have been, yeah, sorry, I might have, you know, talked properly. So what I don't quite remember what I said, but
you suggested that the optical counterpart will be identified as a quasar, and you are producing these figures of associations of quasars with mergers of 10 to the 6 solar mass black holes. My question is there any astrophysical evidence of such association?
Okay, so here I should say, well, technically one should say AGN, right? Because quasars are a specific class of AGN. So, you know, so you might witness so if you have a scenario in which you have for example, a gap in the disk that refills after the binary merge, the binary can start accrete, and then you can witness the black hole lighting up. So it won't be a quasar, technically speaking, right? It's going to be an active galactic nucleus. But so it's just I mentioned this just as a possibility to, you can witness the light up of a black hole, okay, following a merger. So yeah, I shouldn't write quasar there. Yeah, that's certainly incorrect. Yeah.
There's a hand up online. Maybe last comment before we move on. So, Unique, you can speak.
Hello,
I think.
Sir.
Yes, we hear you.
Yeah, okay. So that was a very nice talk. Good afternoon. I'm from India. So my question was that you just explained that LISA could detect or predict the position or the location of where the merger is going to be happen, and could help in detection.
Sorry, it's a very, very difficult to understand you.
Can you write the question?
Yeah, maybe better to write it down. And
I'll do that.
So, okay. Okay. Let's just wait. Maybe you can set yourself already up, Karan.
Okay. So wait. I just stop sharing, so you can share your own.
Okay, good. So maybe because you are panelist, you can actually answer directly in the chat, okay? So that we can move on. Okay, so we will now talk or hear much more about this decihertz band, which is the missing link between the detectors that we foresee for the future. So Karan, please.
Okay. Okay, my voice is going fine, right? All right, well, first of all, I apologize. I'm a little jet lagged, so my voice may stumble a little. but I'm pretty excited about the meeting has been very extremely informational for one part, and the second is the science case of decihertz. Now has many more sort of potential than let's say about a few years ago when we had DeciGo as perhaps the only sort of mission in decihertz that we people used to talk about. My interest in lunar, sorry, is fine. Okay, fine. Sorry. So my interest in moon specifically comes from my interest in decihertz, which comes from an interest in a source that I'll speak about. So here I'm going to speak a little about decihertz, but the image that you see in the background is actually of what we call an intermediate mass black hole. It's the actual gravitational wave, the Einstein solutions to what we had discovered announced in September, actually from this room, the GW 190521. So that's the discovery there. Now, okay, let me see if I can have this Zoom part. Sorry. No, it's still bought. Well, that's fine. This is all the discoveries that we have had with the Virgo and the 2 LIGO detectors in last 5 years. This is the revolution that has happened because of our access to gravitational waves from 10 hertz to 100 hertz. Both the detectors do go to higher frequency, but arguably all the sources that we do see right now is just because we have fundamentally improved around 10 to 100 hertz. The very dark plot here for this for the slide, but the very first signal you can see the time frequency map is the first discovery of gravitational wave GW 5914, and after that there are about 50 such snapshots. All 50 of them are either mergers of 2 black holes, or in some case they are neutron star collisions, or in some neutron star black hole. And it's pretty interesting because we started from having no discovery to all this in a matter of very short time span. And all black holes have been very unique. They tell us a very unique story about the universe, about how the formation happens. So we do absolutely want to see more and more such sources, which potentially would be in thousands before the end of this decade. Now, so this was all we had just from the 10 to 100 hertz improvement. Let's see, does this laser work? Oh, no, it doesn't work. Never mind. Which is if this is the gravitational wave spectrum. Stefano's talk also had this slide, this particular very nice infographic. I think it's from NASA. The axis shows the time or the wavelength of gravitational wave or you can measure that also as frequency. The very right hand side of this plot is what we have ground detected. It is exactly what we have Virgo outside, all the way up to kilohertz, 100 hertz frequency. Then the LISA happens just around millihertz. One thing that we did not speak much about in today's workshop, but most likely a detection is going to happen this decade, is the pulsar timing array that happens around nanohertz. One long-standing question is that perhaps cosmic microwave background can see this very low frequency gravitational waves linking directly to the Big Bang. But in between that, I've tried to squeeze this box, trying to push space between both LISA and 3G. So I apologize to both communities that I'm trying to push the science case here, but that's essentially where this whole idea of moon becomes interesting, that there is a particular gap between the space detectors and what the 3G detectors can achieve. Now, this gap, we call it decihertz, but it's rather sort of a broad range. It can go from almost 0.1 hertz to about 5 hertz. And there is a fundamental challenge. Why can't we have a detector that can reach that stage so easily? Why do we need to have a planning at least 20 years in advance? Well, one such is that any ground-based interferometer that you make, whether it is Virgo at this current sensitivity or something extraordinarily powerful like Einstein telescope, you still cannot go below 1 hertz. And that has to do with just the seismic activities on Earth. That's a very hard barrier to break with the technologies that we understand, right? So let's say the lowest frequency Einstein telescope, in the most ideal case, is 5 hertz. Learning just from LIGO and Virgo right now, it's very hard to reach the design sensitivity at low frequency, even after 5-6 years of detection ability, right? So the fact that we would have 5 hertz is already in principle a little ambitious, right? It will take over the course of time. Now, on the other spectrum, for a space mission like LISA, as we already learned this morning, that it has a pretty extraordinary sensitivity, but you cannot go beyond 0.1 hertz. I mean, you can have some level of detection, but it is not at the sensitivity that gives you any significant signal to noise ratio. You cannot do much astrophysics from it. So basically, you are stuck between this 0.1 to 1 hertz, where neither space nor ground at present technology can work out, right? So this is really the missing link in all of gravitational wave astronomy. Now, my interest, particularly decihertz, comes from the sources which are called the intermediate mass black holes. This is a cover that the Nature had on intermediate mass black holes last year. I can argue with anyone that these are the most interesting sources in gravitational waves, at least for next 20 years, because these are the only sources about which we have no prior understanding from electromagnetic counterpart. Other sources, we still have rough understanding. We have seen supermassive black holes, we have seen we have seen neutron star, and we have seen black holes in X-ray, etc. as well. But intermediate mass black hole is like one of these things that only gravitational wave astronomy can probe. Now, because this intermediate mass black hole happens to be just that mass where decihertz regime becomes interesting, and I'll speak a little about that. So we've had actually done 2 sort of a survey or science case study. One was for the Voyage 2050, which makes a case of every science perhaps we can do in decihertz spectrum. It was done along with the members of the LISA consortium. It was submitted to the European Vision 2050, the ESA Vision 2050, which is perhaps the next generation mission after LISA. One of them was a microhertz mission that was the last plot that Alberto showed. And the continuing study along with DECIGO was done part of the handbook that Stavros had led. It's the Handbook of Gravitational Wave Astronomy. That also includes a chapter. I'm only going to go very briefly through points of this all 3 articles, but I highly encourage, if you're interested, then you should read. Now, the decihertz epoch, right? So we have the current epoch, which is LIGO Virgo. We are going to have LISA epoch 2034. We are most likely going to have an Einstein telescope epoch somewhere in 2030s. Decihertz epoch would have perhaps 4 of the possibilities, of which moon being one, and which we are, of course, going to discuss in the next section. There are other 2 possibilities. One of them we also discussed earlier was the DECIGO, right? So DECIGO in some sense is the sort of penultimate decihertz mission, just because of this frequency it can span through, the sensitivity in those frequency. It's very hard for any other decihertz concept to overshadow DECIGO. So you can almost consider DECIGO as being the sort of the super subset of what decihertz experiments are. But there are other shorter versions, because DECIGO is fairly ambitious. It needs 4 network of LISA-like scenario, right? We are still 15 years or so away from the first LISA being sent. So that is a very ambitious concept. The versions derived from DECIGO is BDECIGO, a shorter 1 constellation version. Another version which we submitted to ESA's Voyage 2050, Vision 2050, was the decihertz observatory, which is still a heliocentric orbit. So you have something like LISA orbiting the sun, and you can make it into a decihertz detector. So that's one possibility. The second possibility is you don't need to go around the sun, because it's expensive, it's complicated. You can do something as a geocentric orbit. So let's say if you had a bunch of CubeSats and you send the CubeSats, make it into a triangular interferometer in space, you can detect gravitational waves with them, but albeit you won't have the sensitivity that we typically speak about in gravitational waves. The third is the moon, and the fourth is something been around for a while and it may ban out, is the atom interferometry. It has its multiple advantage that it doesn't need this sort of a geometry control that the traditional interferometric setup does, but it does have an excellent advantage in the decihertz regime. So all of these concepts are potentially possible decihertz missions. Now, this is the sensitivity. This is strictly gravitational wave speak, because it's a plot that we mostly try to gauge sensitivity by, the y-axis being our traditional characteristic strain in dimensionless units, x-axis being the frequency. The dark black line you see is DESIGO. And you can already see like it kind of outperforms every other concepts, that comes beyond it. But one has to ask, like, do we really need something so sensitive, right? I mean, once we start seeing sources up to redshift 3, redshift 5, I think it does a really good astronomy that we can do out of it. LIGO, Virgo detectors don't even go that far, and we still learn so much. So we don't really need to be super sensitive across decihertz region. Something like Decihertz Observatory, which is only one constellation, can have at least an order of magnitude lower sensitivity than DESIGO, but it still works out pretty good. BDESIGO would be 2 or 3 orders of magnitude worse, but it's still decent to cover the space between, post LISA and then any other, third generation detector that comes in. And I have only one lunar concept here, GLOC, and the LGW and LSGA would be performing better than this one at around decihertz, but it won't still be performing better than DESIGO. Right? That's just the level here. Quickly about this Voyage 2050 idea. So this derives completely from the success of LISA. So assuming LISA works, assuming LISA had this fantastic 10, 12 years of science, we learn something out of it. And then one of the things we can aim to have achieved is, let's say, a factor of 100 improvement in acceleration noise. It sounds too ambitious at this point, but looking ahead, let's say by 2050, is something within the same technology that we are trying to, perhaps get. We need better lasers. The laser power has to be at least about 10 watts, which is I think about a factor of 5 more than what LISA's wavelength would be. We need telescopes that have to be slightly bigger than what LISA has. But most fundamentally, the idea is that you need shorter arms of LISA, right? If you have about 25 times shorter arms than what LISA has, you start accessing the decihertz range science. So this is something which potentially can be achieved in post LISA scenario. If we don't want to have something which, I mean, the moon and the atom interferometry, which still relies on other technology that to be tested, this one comes as the sort of a natural derivation of LISA itself. Now, the science case, why make all this attempt to go in this tiny, blue box that I showed between? Because a lot of science that decihertz can access, we do access already with LISA, partly, or we do access that with 3G. It's the matter of how well each of the science you want to have, like, what is the level of sensitivity you want, how far you want certain sources to be seen. So specifically, this plot is showing the gravitational wave frequency on the x-axis. The y-axis shows time before merger, how long does it take. So on the farthest end is you have this ground detectors. On the left hand, you have the space missions. In between is this decihertz range. Decihertz is sort of a vague range. You could go from 0.01 hertz to about 1 hertz. I'm just going to call all of that as a decihertz potential science. Now, neutron star, they start entering decihertz, like a year in advance. You had any decihertz detector, you're going to see them at least 1 year in advance just because of the time it can spend. You can see that all the way at 10 hertz, they spend about a couple of minutes, which is what LIGO Virgo is able to see for binary neutron stars. But increase the mass of the binary, come to 1,000 solar mass, where we start thinking about intermediate mass black hole. Even at 1 hertz, they spend less than couple of seconds, right? So you simply don't have enough duration of the signal in band, so you almost cannot have a sensitivity of it. Go to 10,000 or 100,000 solar mass, you simply cannot have any of those sources in ground base, right? The frequency is just much below for the time it needs to spend for you to record enough signal to noise ratio. They can be in space-based detectors, but what happens in LISA is that 1,000 hertz system would only go through in spiral, but the more interesting merger ring down would happen outside LISA. That happens for 1,000, that happens for 10,000. So essentially, in terms of intermediate mass black hole, LISA seeing in spiral merger ring down happens only close to 100,000 solar mass, right? Everything before that, it only really is in spiral. So the science of intermediate mass black hole, if these are your sources, decihertz is the only potential detector to see it. Now, why we want to see an intermediate mass black hole? I mean, Alberto's talk gave this nice overview. There are these seeds of first generation stars, or even the supermassive black holes that we see at the centers of galaxy. The second science also covered nicely, which is the multi-wavelength gravitational wave astronomy. Think of the same way as looking at something in the universe in radio, in X-ray, in visible light. You need all those three information so you better understand the source. The same holds even with gravitational wave spectrum. The only difference being that you don't see the source at the same time as you would see in electromagnetism. You see different dynamical range. So first it will enter low frequency, then it over the time a source would go into high frequency. So every spectrum looks at the evolution of an astrophysical source in a different viewpoint that was not available to the other band. For example, if we had a GW 190521, the 150 solar mass black hole, the biggest merger that we know so far, only spent 0.1 seconds or so in the LIGO-Virgo band. Makes it very hard to do much understanding of what the origins of such odd binaries are. The same source actually LISA would not be able to see because it is so far at almost 6 gigaparsec, close to 5 to 6 gigaparsec, that the signal to noise ratio in LISA becomes very, you'll see, but it's all order of unity that the signal to noise ratio starts becoming. So this is where decihertz again plays importance, because every source that you're going to see in ground, no matter what signal to noise ratio, no matter how far it is, it default enters the decihertz band. Whether it's binary neutron star, whether it's black hole, whether it's neutron star, black hole, all of them are default multi-band sources. So we can imagine an entire era where you are going to have hundreds or thousands of detections already pre-known exactly with merger time, exact information, sky location, etc. And that's a kind of gravitational wave astronomy you can only do with decihertz detector. It opens a new test of general relativity. It also gives us direct insight on the astrophysical environment. You would know the eccentricity, you would know the mass distribution around which the binary is coming from. Again, that kind of thing is very hard to do with LISA because it's just a signal to noise ratio, not going to collect so much. And there are many, many nice papers written since, Alberto's, debut paper on this. The another point of decihertz, which is, multi-messenger astrophysics is our catchphrase. We want to use that for everything in gravitational wave astronomy as much as we can. What is interesting in this decihertz is it opens the case of tidal disruption events, something such as, let's say, a white dwarf star being eaten by an intermediate mass black hole, so about 1,000, 10,000 solar mass. Whether such sources exist in nature is an unknown, but presuming such sources do exist, a neutron star, an intermediate mass black hole, an intermediate mass black hole, and white dwarf, that kind of disruption, you see a gravitational wave emission that would happen near decihertz for the sources, but they would also be emitting, just before the merger happens, the other compact star would get shredded. This is nice numerical relativity visualization for a neutron star black hole. You will see this kind of nice dust cloud that would happen. The flare would happen at super Eddington limit. You should be able to see such sources. And based on the models that you pick, you can at least see thousands of such sources with a decihertz detector every year or so. Now, this is the plot that we were discussing about, where in the cosmic horizon decihertz detector really plays in between a LISA and Einstein telescope. Now, the y-axis here is your cosmological redshift. Your x-axis here is the mass of the binary. Just presume everything here is the mass of the black hole at first order. The radius that you see down here is what LIGO-Virgo can see right now. Like this is the entire spectrum of what we can see in terms of mass and in terms of how far in the universe you can see. The same detectors, if they go through another round of upgrades like Voyager, they can see little farther away, like up to a redshift of 7 to 8. The plot all the way on the right just shows what else is happening in the universe in that time scale. So we have the peak of star formation, we have the dark energy dominated era that is already being seen by LIGO-Virgo. But really, none of these detectors can go to the first stars and galaxy. For that, you would need an Einstein telescope. That is an improvement. It's only a factor of 2 in terms of frequency improvement. It goes from Virgo detector being 10 hertz to Einstein telescope being at 5 hertz. But the amount of universe that you can see now almost goes to, like practically any source in the universe in this masses. If they are in binary, Einstein telescope can see it, right? So that's a statement. Now, the same thing in LISA, actually, that sees practically everything. It sees as far as almost up to cosmic microwave, not cosmic microwave background, but everything since then. There is no astronomy telescope that can see the universe as far as LISA can see. You can reach the 500 redshift, that would be nothing. But if anything happens, we know that lambda CDM is not correct. So this is already what we are going to see, regardless of a decihertz detector happen. This is 2030s gravitational wave astronomy. Now the gap in between, that Alberto and Stefano mentioned, is this sort of this V shape that is happening that none of the detectors are able to reach. Put a decihertz detector there, this is what it looks like. It not only covers the whole gap that was there between ET and LISA, it does something interesting too, because LISA is only a limited time mission, 5 year, 10 year, maybe 15 years. But after LISA, if you still had a decihertz observatory, you do see 10 to the 6 solar mass binaries, pretty much like redshift 10, which is as good as the entire universe, for us to think about. So these are good post-LISA mission alternatives to continue the science questions that we have had in LISA itself. The final point, which we really want gravitational waves to sort of probe from a fundamental physics experiment, is we want to find theories beyond Einstein. We want to find beyond standard model physics, understanding of dark matter, etc. So one thing a decihertz experiment actually does very well, better than any other experiment, is look for this sub-solar mass binary black holes. So if you had like 0.1 or 0.05 solar mass black holes, dark matter candidates or some form of the other, and actually LIGO Virgo does search for them at this point, these sources you can see at a very high cosmological rate because of a decihertz excess. Then there are these interesting things happen that if two black holes merge, the bigger black hole now is spinning faster. So if there is a bosonic field around it, it sort of gets this monochromatic gravitational wave emission from that. The mass that it can access, if you can see an intermediate mass black hole, is apparently very interesting to particle physics folks community. So that happens only in decihertz because you need an intermediate mass black hole to have formed to find that sort of dark matter fields. And finally is the stochastic gravitational wave background that we wish all gravitational wave detectors can see. The advantage decihertz has is because you know the merger rate so well that you can almost know what astrophysical background to cancel out. And then whatever you are left with is your stochastic cosmological background, right? So that kind of understanding decihertz adds because the merger rate is known with such high precision. So in conclusion, observing 0.1 to 1 hertz, is this a very tiny range in this big gravitational wave spectrum that we already are familiar with, but it advances fundamental physics and astrophysics in a way that it's just something that we cannot ignore, not because we don't have an experiment, but we do need something there. The good feature is it has a strong synergy with what we already are going to build. We are going to build Einstein telescope. We are going to build LISA. Decihertz has a great synergy between the two cases. It's not that it sort of overshadows one over the other. Many promising detector concepts exist in decihertz again. It's just everything is unknown, whether we speak about moon or whether we speak about atom interferometry or whether we speak about post-LISA scenario. This technology is not something that we know how long it's going to take to pan out. So that's one of the statements here. But what I do like is this, so it's sort of cutting down here because of the zoom, but it's the number of publications that have cited decihertz since the first discovery of gravitational waves. And actually, if you could see 2021, it has this sort of exponential rise. I guess because 2020 had less papers. So 2021, I think people are pushing, but it's a constantly increasing trend. More and more people are interested in decihertz science. So that's about it. Thank you.
Thank you. Great talk. I'm convinced. Let's do it. So any questions for Karan?
Sorry, Karan, the plot that you showed, this plot. So this is for that Decihertz detector that you mentioned in that study, right?
This is for this detector.
All right. Okay. So it's not for any of the lunar things we're talking about.
That I will show in the next talk, in next hour.
Okay. Thanks.
I'm puzzled about the calculation you mentioned about intermediate black hole and tidally disrupting a white dwarf. As far as I know, we haven't seen even one.
Yeah.
So on what did you base the statistics? So far, we have only fairly strong upper limits because there is extensive surveys in electromagnetic surveys in all bands for such events. And there are none. Well, there may be one, but it's not intermediate mass black hole. It is a white dwarf and 10 to the 5, 10 to the 6 solar mass,
Yes.
which is in a different regime.
Yes.
So I'm just puzzled.
So,
I admire, or put it differently, I admire your imagination.
So yes, the statement can be, we can see 1 to 1,000. Let's say we start with that. It's a sort of very upper limit calculation, estimating how many, let's say, IMDHs we could have. Just 1,000 also we don't know, but let's say assuming that we have some count, and then we make a count of white dwarf and neutron star and regular black holes that we see, create some sort of a function, how many of them interacting together, coming with a very crude estimate. But yes, that number could very well be 0. I agree. But at least this eliminates out, because one thing is, if we don't see any of it in gravitational wave, let's say we don't see in electromagnetic, if we don't see any 1,000 plus neutron star, then we do kind of know that, well, globular clusters are kind of tricky. Or if we don't see 1,000 plus a black hole of 10 solar mass, then again, globular clusters are tricky for these sources.
Okay, is there another question? Okay, if not, I say we first thank all of the speakers again of this session. It was a wonderful session. And I suggest that we reconvene at 4:40. Okay, thanks.
4:40, right? Yeah, so yeah, oh no, that image was black hole neutron star. It was not that. That was for the LIGO's black hole neutron star. Yeah, so that was black hole neutron star. Sorry. Yeah, this is the latest discovery that we saw. That LIGO, the black hole neutron star, but not the 1,000 plus. No, that won't happen. Yes, this is just I should have mentioned, just an image.
Yeah.
Yes.
Well, yeah, we want to be here. So we're 10 minutes late. Okay. No, you were doing very well. Actually, all the sessions going well. But you have these type of questions. Yes. Good to see you. Yes.
No, sicuramente è stata tipo una delle come è stato studiato in Italia. No, infatti,
Okay. Yeah.
You have to wait because you have to. I know. Very precise, precise. According to my standards. In realtà, in qualche senso ovviamente sì, perché non c'è il rumore per niente, ma in questo senso sì. Dipende, ovviamente le tempistiche sono sempre lunghe, non si può fare niente. In qualche senso si può andare avanti più veloce con qualche cosa, ma l'altra cosa ci vuole molto di più. Oh, okay. I guess we can start. No, in reality, I'm sharing on because I'm logged into Zoom. So I'm also logged. Yeah, it's the easiest because I can use my computer and yeah. Yeah, and then I share screen and that's it. Okay, just a few seconds because people here are still finishing their coffee. But I think we should start soon.
I can take and then afterwards
So we continue with now the propositions. This workshop was meant, first of all, to have a discussion between these propositions. Now we enter into this issue in France. And please, Jan, tell us.
Thank you. Okay, so I'm going to present to you one of the three concepts that were proposed last year in response to different calls in Europe and the US. So I'm talking about the lunar gravitational wave antenna. And we have already heard today that in reality, one of the targets of these detectors, a very rewarding target would be to cover the decihertz band. Not to say that other frequencies are not interesting to cover if possible, simply because you can always enter synergies with other detectors in any case. But the decihertz band is uncovered by other observatories so far. Also by terrestrial detectors cannot be observed. So I think that should be an important target for us. Okay, so okay. So this is really what we are after. That is the fundamental mode of vibration. And in reality, you know, for a simplified lunar geological model, at any frequency, this is how it looks like. I mean, here is shown what we would identify as a spheroidal vibrational mode of the moon. There are also toroidal modes that can in principle be excited by gravitational waves. And you can now observe this kind of vibration simply by deploying a seismometer on the surface. You can call it seismometer. In the past, it was called gravimeter in another experiment. Or you can also use, for example, seismic strain meters. We are going to hear about this later. With the lunar gravitation wave antenna, I'm going to talk about the idea to use a seismometer for that, or actually an array of seismometers. Now, I don't have time to really go into details about important details actually about the response of the moon. Just a Gedanken experiment. If the moon were frictionless fluid and you put a ship on its surface, and on the ship you put a seismometer, then if a gravitational wave passes by and causes deformation of the moon, of the liquid moon, you would have no signal in your seismometer. Why? Because the test mass of the seismometer would just follow, like all the fluid particles around under it, that kind of tidal force, and essentially generate no signal inside the seismometer. So this is just to tell you, it is not just about deformation of the moon and to describe it. You really have to understand the experiment as a whole, how it responds to a tidal force like a gravitational wave. And there are different approaches to simulate such a situation. But the good news in the end is that the moon is not a liquid ball. And in fact, what it also has is elastic resonances, which we have seen already in at least in Philippe's talk in form of peaks in the response, in the elastic response of the moon to, for example, moon quakes. So all of this can be exploited, but modeling this well and accurately is very tough. And of course, in addition to that, the moon is not a homogeneous body. It is at the very least having at large scales already the radial heterogeneities, a layered structure, and on smaller scales for sure also significant lateral heterogeneities, and all of that goes into the response calculation. And we honestly do not have at the moment a reliable model to tell you what the gravitational wave response is between 1 millihertz and the hertz. We do not have that. And this is partially because of lack of understanding of the interior structure of the moon, but partially also because we do not yet have, we haven't done yet the theoretical and numerical work to describe this response accurately, even based on whatever we currently know about the moon. Okay. Now, the idea I'm going to describe has a history. It's not new. In fact, we already have a lunar gravitational wave detector on the moon. It was called the Lunar Surface Gravimeter. Now, that was coordinated by Joseph Weber, who is considered as the founding father of experimental gravitational wave detection, who invented the Weber bars. Now, Apollo 17 brought this instrument to the moon. And unfortunately, well, in hindsight, we didn't lose a lot of gravitational wave science, to be fair, but it was brought to the moon with a design flaw, which actually reduced the sensitivity greatly of that instrument, which didn't, give it any ability essentially to observe low frequency vibrations in the millihertz band, for example. Now, in hindsight, I say the damage was not too high for gravitational wave science, simply because today we know that the level of sensitivity that instrument would have had in the ideal case would have been orders of magnitude away from what we need to see gravitational waves. So in that sense, I think it is mostly a loss to geophysics, because that instrument clearly would have told us something more than we already know from other Apollo installations. Okay, LGWA. So here's the basic idea. We propose to deploy in a kilometer scale array. This is, kilometer scale is not very precise, obviously. That has a reason, because you really have to design the dimensions of that array according to your local properties in terms of seismic speeds, for example, in the local medium, but also depending on the sensitivity of your instruments. They can influence this, the size of the array, and how you would optimize that configuration to, because this is the purpose of this array, to be able to distinguish in an optimal way between a seismic background that is produced on the moon by meteoroid impacts and so on and so forth, and the gravitational wave signal. So in this optimization, something very similar we have done now for Virgo, optimizing sensor arrays for noise cancellation. This would have to be done as well for LGWA, once you really know what the seismic speeds are in the most interesting frequency band for you, where you have to provide noise cancellation. Anyway, these sensors would monitor the vibrations of the moon. Let's say we are targeting 1 millihertz to a few hertz. And this whole idea emerged first as part of this ESA call for ideas how to make use with scientific missions of a European large logistics lander. And of course, we have discussed this a lot today. I will not add too much about this anymore. What we do know is that the moon is an extremely quiet place. Maybe it is the quietest place that we can ever scientifically exploit. And it has other advantages. It might be, at some places at least, the coolest object in the solar system. At least it is for sure competing for that position with few other solar system bodies. And this is a unique combination. And then it happens that this one is in our neighborhood. So good news. So far, so good. And there's, of course, our opportunity to do gravitational wave detection. Now, we have heard a little bit about this already, but we currently, with a team that we put together to think about the technologies and to think about what sensitivities we need for the instruments, we do not believe that we can do the deployment at any other location but permanently shadowed regions. So that is a very big constraint on the mission, which causes a lot of headaches on other parts of the mission, if you want. But it really helps us to get to be able to promise, in some sense, or target at least, sensitivity improvements as we need for this concept, compared to seismometers that IPGP has built or is going to build for planetary science. So this is a huge technological challenge, and we believe the permanently shadowed regions which exist at the South Pole and at the North Pole of the Moon, regions protected by craters. Now, why this? Because it provides a cryogenic environment. So we have heard that, this is good for different reasons. We have heard that there might be even seismic disturbances and even ground tilts that might be connected to thermal effects. Now, this you avoid, first of all, in a permanent shadow. But in addition to that, there are regions, there are some of these craters that are so cold that they provide you a temperature which is continuously, let's say, below 40 Kelvin. Now, that is a huge advantage when it comes to cryogenic instrumentation, because it allows you essentially with a rather simple cryocooler compared to other scenarios, with a rather simple cryocooler to get to really interesting temperatures for you instrumentally, which is 4 Kelvin. So at 4 Kelvin, the world is changing because you introduce superconduction with all of its implications, like squid readouts and so on and so forth, as options for your experiment. And that is really where you can think to achieve the breakthrough, together with very clever mechanical concepts of these instruments, together with highest quality materials to realize the mechanical structure of these instruments. Now, and here the thing, here the main headache that we now have with this kind of concept, and this is, I think it might really determine our timeline in the end. If you're on a permanent shadow, then you have no sunlight, then you have no power. Typically, you don't have power. Now, this is not a new problem. In some form, it has existed since Apollo, because you anyway have to survive 14 days on the moon, because that's the lunar night. So this is not quite a trivial problem, and it makes a huge budget difference, for example, between missions that are planned to last for 10 years and missions that are at least nominally planned to be 4 months or something like that, or even less. So there's a lot of money that has to go into the mission to guarantee long lifetime. And you can do this with nuclear power. That was what Apollo missions used with every of their station deployments. Or you can try something completely new, which is typically not an option for most missions. But if you are at the lunar South Pole or North Pole, then you can get illumination by the sun, which exceeds 50%. It can even get to 80% at some places. So that allows you essentially to deploy in a sunlit part a solar panels, solar cells, and they would convert sunlight into a laser beam or microwave beam. They would get this into your permanent shadow, and then you have a receiving panel that would convert it back into electricity. And then you would maybe continuously, charge a battery or whatever you can do. I'm not at this point expert enough to say how this would have to be done. But this sounds very good. But it is beyond, and nobody has tried this ever in space. I mean, there has been some work done on Earth, but this would really take time to be used in a mission. So this is the situation. Now, to say a few more words about the seismic background, because that's such an important discussion. So at low frequencies, by which I mean below a few tens of millihertz, I think the situation is okay from our perspective in terms of gravitational wave detection and seismic backgrounds. I mean, we have seen a few details about this already from Philippe today. I believe that it is likely that we can do gravitational wave detection on the moon below a few tens of millihertz without any other measures in terms of cleaning up your data from a seismic disturbance. Now, Philippe has outlined a bit that maybe we shouldn't be too confident about this, but anyway, I think for sure there are things to be understood, but the situation looks much more promising in at these low frequencies from that perspective. So, however, certainly at 0.1 to 1 hertz, the situation is quite different. And this is not only because you might have seen also in plots we have seen today that the seismic background becomes stronger, but it's also that the gravitational wave response becomes weaker. Because while the large surface vibrational pattern is always the quadrupole mode with the same gradients, if you want, across the surface. If you look in radial direction, the higher order modes, of course, have many more nodes, and effectively the response of the moon, or you might also say the cross section of the moon to gravitational waves, will just decrease with higher frequencies. So that makes your signal, your response, weaker at high frequencies, and then you have like this seismic background to compete with. So it seems very, very likely that we will sit on a seismic background in the band 0.1 to 1 hertz. So if you come with a concept that relies on the response of the moon to detect gravitational waves, then for that band you have to come also with a mechanism to remove remove is not possible, but to suppress that background for you in your data. But just to mention, we have heard this, I mean, meteoroid flux is probably one of the likely candidates, let's say, to produce a dominant background at that frequency. I won't say much about our instrumentation because we will see more about this tomorrow. Just to mention that there is I think a very beautiful concept, at least for such an instrument. And one detail that I want to mention at least is that developing such an instrument on Earth is in a normal lab environment impossible, because you are designing an instrument that has to work in the seismically lowest noise environment that the solar system can offer to you. In that environment, so a system that works in that environment is not supposed to work in a terrestrial environment where you have like even where the weakest background noise that you can find anywhere is essentially with an SNR of 10,000 or 100,000. So of course that doesn't make that doesn't work. That's simply not the situation for you to even demonstrate the performance of that instrument in terms of sensitivity. So you have to go underground to get a really quiet natural environment, and then in addition to that, provide a seismically stabilized platform to run and test your instrumentation. So now, doing that, if we're able to do this, then we're ending up with the sensitivity curve. So the blue one is something that you have seen so far already in some of the other talks. Now, I'm also adding this gray spectrum there. So what's that? So here's the thing. I mean, if we want to be really fair, since we are quite oblivious to the properties of the moon in terms of how it responds at high frequency to gravitational waves, because you really have to understand the elastic properties in detail. We are talking not only about seismic speeds, you have to understand damping, which is actually important, and other features, later heterogeneities. So if you take the very worst scenario that you can imagine for the response of the moon, which is unlikely, but if you just assume that, then you will end up with this gray response curve and sensitivity, assuming the technologies that we propose. So we instead believe that the response will be such that we are getting at least very close to this blue curve, so that we are not sacrificing too much there. But just to, this is serving maybe to people who are working on this, that there's a lot of work that needs to be done for us to be able to present a good model. I am, we have talked about the science already. I'm not saying much here. So of course, already mentioned. I think we are closing the decihertz band or the gap between LISA and ground-based detectors. That's great. There's a lot of science associated with it, as we have heard today. There's maybe one interesting calculation that was done by a student from Columbia University, and she looked specifically with the latest population models of binary neutron stars and solar mass binary black holes. She was studying how many signals we could see with LGWA, with a sensitivity, with the blue sensitivity curve that I showed on one of the last previous slides. So with the latest population models, which have a little bit reduced binary neutron star rate locally, you would still be able to probably see 2 neutron star mergers. Of course, this is not a precise prediction because we have Poissonian, at the very least, Poissonian errors on the local merger rate. But these 2, as we have seen, even 2 would be great, simply because you could run this scenario of giving an alert to ground-based detectors. And of course, you would maybe like to have 10 or 100 instead of 2. But I think I can easily imagine that it will be 100, that it will be 10 instead of 2, because we are really not being extremely accurate. You might also argue, well, it could be 0 instead of 2. That is unlikely, because with GW 170817 we have at least one example which was so close that we would have seen it with LGWA, and it would have merged to be seen by gravitational wave detectors on Earth. So in that sense, 0 is not correct. And this is also the numbers per year. So the lifetime, of course, of the experiment has to be considered here as well. And here you see, by the way, the sky localization that you would be able to provide, which is at least for one of the being simulated binary neutron star mergers here, sub-square degrees. I think that would be, of course, huge for of great use for ground-based follow-up studies or electromagnetic follow-up studies, of course. Okay. Then, okay, again, briefly, because we have heard so much already about the science, there are the galactic binaries, white dwarf binaries, mostly. Of course, LISA would be able to see all of them, essentially, that you can possibly see, unless you are sitting on this famous background that they produce. But LGWA would be able to see hundreds. The real question is about the mergers of white dwarf binaries. They are, even though we have millions maybe of white dwarf binaries, it doesn't mean that we see a white dwarf merger even per year. So it is kind of unlikely, but if you are lucky and with long enough mission lifetime, you might be able to actually catch one white dwarf binary merger from galactic binaries. And so then that would, of course, be a huge observation to make with LGWA. Okay, I want to stress one thing, and I mean, Stavros mentioned this after the speech today by Minister de Pedis, that that the environment of a gravitational wave detector is extremely important. So already here on Earth, we are really struggling with all kinds of environmental couplings and effects. I mean, we're not just talking about seismic fields, about anything essentially that you can imagine to happen in nature is kind of important to gravitational wave detection if it happens close enough to the detector. So this will be quite similar, maybe not so extreme, because we are not entering these very good sensitivities that LIGO Virgo have in terms of strain sensitivity. But still, you can be sure that the geophysical environment of LGWA and any other gravitational wave detector on the moon would be extremely relevant to the experiment, not only in terms of seismic, but also in terms of temperatures, magnetic fields, even micrometeorite impacts or cosmic rays. So you can add to this. So anything that happens between now and 10 years from now in terms of lunar exploration, science missions to the moon, just to understand the environment there's of course already a great deal of understanding, but maybe not enough for us to really draw final conclusions about potential issues and interference with our experiments. So it will be extremely important. And luckily, of course, we have heard that also from Francesca, especially, who gave this huge overview of different missions that are under consideration. Of course, everything that happens in the next years will be extremely important and maybe crucial for any lunar gravitational wave detector mission to move on. And so my last slide, I think we have heard, of course, that LISA might have a lifetime even of 10 years and more. Now, this is definitely, in principle at least, a big plus of lunar gravitational wave detectors, that they can have long-lived installations. And of course, there is no hard limit to it in sense of orbital stabilities and all of that. Of course, powering an experiment is, I think, the issue. Like, how long can you realize that? There might be other things, effects that limit your lifetime. The Apollo seismic experiments, as far as I know, the 4 long-lived stations were all going on, and they were essentially switched off. I mean, the data taken was switched off essentially. They could have probably provided data for some time still. So we have good experience with, in principle, with realizing long-lived experiments on the moon. But okay, I think this is a potential advantage for lunar installations. The detector motion is peculiar because you have this 28-day rotation of the moon, which is faster than the orbital period of LISA. That is an advantage for some observations to get a sky position essentially of your source. And I think for lunar gravitational wave detection broadly, the role of LGWA will be to be a pathfinder in that sense, a first mission, a first generation detector, which is not, because it seems to be technologically at least the least complicated project. I mean, there, of course, you can argue. I think many people would like to argue about this point. But on the other hand, I think that all the other concepts rely on seismic sensors of LGWA sensitivity to function properly, be it Glock that we will hear about or LSGA that we are going to hear about, simply to understand the seismic background noise that might limit your sensitivity. So, and at this point, I want to stop. Timeline, of course, would be a fantasy at the moment to present, but I think just knowing myself at the moment what work we have to do, there's no way this will be deployed before 2035, and probably we're looking at longer timelines here. So just to clarify this point, and at this point I want to stop. Thanks. There's one there.
The response of the moon in this years to 120 not well known, not understood. Is it just a question of calculation, or do we need some more critical data? And how much is the influence? What is the implication for this?
Yeah, so the question was because I mentioned that the response is not really well understood, and where this uncertainty comes from, if it's from missing information or understanding of the moon. So one, again, it's a little bit of frequency dependent point. So I would say, of course, we do not have a very detailed understanding of the lunar interior, but we have some understanding of the lunar interior. And I think it is enough essentially to make relatively good predictions of the response at low frequencies, which I mean, again, where you can resolve individual known mode resonances. Now, we might not really know exactly where these frequencies are. We might not really know exactly what the Q values are, but qualitatively, I think we can provide some reasonable response model at these low frequencies. The problem with the higher frequencies is that there you really have to enter into details in terms of later heterogeneities. We have seen today by Mark essentially on his maps that there's a lot of heterogeneity also revealed by Grail and so on. So I think these are points that have to be really included in quite complicated models, actually, to numerically complicated models to get the response correct in the decihertz band, especially. So I think there we are really lacking information, but also we haven't set up really the numerical tools to be able to use any information that we would have. I mean, there's nothing at the moment at these frequencies.
Questions?
in fact, it is more a comment, but just to. So what we really know is that between say 1 Hertz and 10 seconds, seismic wave equation do not apply on the moon. In fact, it is more a diffusion equation. And we are in a complete multi-passing scattering, I would say, and therefore I think there is no way to predict the seismic waveform with a few sensors. Really, I believe that it will be extremely challenging to demonstrate that with only a few sensors, you can correct anything, because you just do the experience. You go on a volcano and you put 20 sensors and you try to model one seismometer, okay, with 19 other one, it will never work.
Okay, so I think this is fantastic. The last comment I like because it points
go
me
on the
to
volcanoes,
where I have to go. But
you can go there because it is almost the moon in terms of scattering of
okay,
seismic
very
wave.
good. Thanks for that comment. That is a very constructive comment, actually. So, on the other hand, of course, if you in these materials that don't even behave like an elastic material anymore, where you have a lot of scattering and so on happening, the question is still, what is its response to gravitational waves? I think that is the first point. Interesting to address. Then about the noise cancellation techniques and so on and so forth, that's another issue, of course, that you would have to address in such a medium. To that, I currently have no answer, but I mean, your volcano, sorry, not Vulcan comment, your volcano comment.
No. I think it is a good analog. I have another question, which is more, okay, when you made the introduction, you say that if we were on a liquid planet, we will see nothing. So, and therefore, the fact that we have 50 meters per second shear wave velocity at the surface of the moon. So if you prefer, if you put anything on the surface of the moon, unless you make a pillar of 30-meter depth, okay, but say something with 1 meter depth, you are on a material where the seismic velocity will be 60 meters per second. The shear wave velocity will be 60 meters per second. So is it relevant or not? Or do you believe that there is a possibility that this low velocity zone will decouple in some ways the gravitational wave signal of the bedrock from the surface?
I doubt it, because I think such a thin layer must respond to some gradients, and of course the gravitational wave would not produce a significant gradient across that layer. But I don't. I mean, it's always worth to think very carefully about these
because
things.
you see, but again, it is just a real-time question, maybe, because we are discussing so small deformations that at the same time the solid friction will lock the response. So we are not completely in an elastic continuum, and I can imagine that below a given threshold, then the grain-to-grain solid friction might lock everything.
Yeah, I mean, we will see. I mean, ideally, in some sense, what we want is an infinitely stiff body that doesn't respond to gravitational waves, because then what you have is essentially a LIGO detector formed by two test masses, one test mass, the moon, and one test mass, the proof mass inside the seismometer. And you would have the full baseline of 1,700 kilometers to cause you a strain signal. That would be ideal. And I mean, all of these considerations really, but by the way, friction is good for us because it is causing a phase between the response and the free mass response. So that phase actually gives you a stronger signal than you would typically get. So any friction is wonderful for us, except for on the normal modes. Okay.
I have raised my hands, but yeah, can I speak?
Yes, we hear you. Yes, please.
Yeah, okay. This is Ho-Jung Pak of the University of Maryland. I'd like to make a few comments. So this lunar motion in response to the gravity waves cancels the test mass response to the gravitational waves. This is a problem. So moon being, so as a moon, the entire moon is a gravitational detector, but then the test mass suspended on the moon follow the motion of the moon. So this cancellation, we are just trying to understand this, actually the full three-dimensional analysis, we are carrying that out to see how much cancellation actually occurs. This is what Yan has done, but we are doing independent calculation using the spherical harmonics and so on, with the density variation as a function of the radial distance from the center of the moon and so on. But I'd like to make a few comments. I have been always interested in using the entire moon as a tensor gravitational wave detector. So if you have test masses located at 6 places, let's say that Cartesian coordinate pokes through lunar surface, so North Pole, South Pole, and then 4 other places on the equator. So if you combine the motion, three-dimensional motion of these 6 test masses, you detect all the tensor components, and you have extra degrees of freedom. So anything, if there is the seismic event, you don't expect that it will satisfy the traceless condition of the tensor, plus extra requirement only gravitational wave will satisfy. So you can reject non-gravitational event, non-gravitational wave event. Although there is a constant seismic background, which we have to, I don't think we can overcome in any manner. But so this is a much more challenging, but having the 6 test masses spread around the entire moon, and these accelerometers will be 1,000,000 times more sensitive than Apollo seismometers. So probably 10,000 times more sensitive than LGN seismometers that we are also developing at the University of Maryland. So of course, this is a very challenging tall order, but potentially we can overcome this seismic noise, just reject the seismic events.
This was an old idea. Probably you were among the authors. Yes, it was among the first ideas that came up, and probably you were among them. Yes.
So this what this LGWA is trying to do is the first step toward the ultimate goal.
Yes. I should say, okay, one very quick comment, because I think it's time for the next speaker. But when it comes to the response of, the difference between moon and the fluid, I think if one studies the papers carefully, there's actually already the solution, I think, an answer to that, because there are these technical questions about choice of coordinate systems. There's TT and local Lorentz, and just for people who are used to these things. So if you make a calculation local Lorentz, then the gravitational wave field couples to the mass of the moon and to the mass of the seismometer. But if you operate in in TT gauge, then the gravitational wave couples to shear modulus gradients, and the test mass of the moon doesn't have any response to gravitational wave because it's counted as a free-falling test mass. So just to say that there are, I think, already the answers out. One just has to discuss maybe at another time more carefully to convince each other that we understand that part at least. Okay.
Thank you. So let me also share my screen. Since it's a mixture of different things, my slides will be sometimes a little bit talkative, but I hope I have things that are useful. Now, LSGA, Lunar Seismic and Gravitational Antenna. The concept is based on fiber distributed acoustic sensor system The goal is, as probably all of us, plenary, gravitational wave geoscience studies, and even acoustic studies. Participation in topical themes, in Artemis, in ESA, and it was for Jan and myself were the reply to the L3. Now, why go to the moon? It has been said again and again. I will not lower seismic background, better localization precision, multi-band analysis, and the independence of the backgrounds when we will try to look for instance, stochastic gravitational waves. I have some slides about that. But I mean, this you've heard and had very nice talks about them. How can we detect? Again, two methods. One is to use the moon as the detection body, and the other is to detect the gravitational waves directly. I will spend more time, although in our group we're discussing both solutions, I will spend more time on the first concept. So based on historical studies that have been said already by Jan, Weber, Dyson, Ben-Haim, and also more recently a thesis and a publication by Mastorovich, I will show also some kind of work in progress about this analysis that was asking whether we have or not. And the second concept, of course, is direct detection of gravitational waves through laser ranging techniques. And we'll hear tomorrow also by Simona Dell'Angelo nice ideas about it, but I will say very few things about it. So the first step is you deploy an L of 10 by 10 kilometers with engineered fiber distributed acoustic sensors. You calibrate it essentially with an FBBZ seismometer, and also you try to accompany this with a distributed temperature sensing network, always through fiber. The advantage you will have with that, and I will say very few things, you hear more tomorrow about the concepts of fiber of the FDAS, is that you can deploy, you can have, let's say, if you have a 10-meter gauge length, you can have 1,000 sensors. So with 1,000 sensors, you can have stacking, you can increase your sensitivity, you can have directionality. That's the one thing. And what we get these days by, for instance, our colleagues that we work with is of the order of 10 to the minus 13 per square root of hertz in relative strain. And this for each detector, for each sensor, for each 10 meters, let's say. So, of course, you can, again, follow up for temperature sensing. We also arrived completely independently, and I will show you a study about it, that we have to operate in a permanently shadowed region. And it is easy for us because we have one interrogator unit and then the fiber. So the interrogator unit can be outside the permanently shadowed region if we can, and then why not, probably also a sort of dead part, and then the fibers, the sensitive fibers inside the PCR. And of course, but we'll still probably need some protection by thermal. Well, let's say the public image of that, you have the interrogator, you have the fiber, you launch a pulse, you get it back, and by getting it back through Rayleigh scattering, you have seen any changes in the refractive index, and this is sensitive. And essentially, it is not changes in, I'm sorry, I said it wrongly. Essentially, any either thermal or vibrational, acoustic, if you wish, heat essentially changes the strain of this 10-meter gauge, or actually it is smaller parts you can do every 2 meters or every 1 meter, and then you add them up and you get your gauge length in order to study it. And that's the way you do when you deploy the fiber. Then the other, this is, as we said, concept one. Concept two is the lunar ranging strain meter. where you have here, for instance, again, probably you can use the same L, 10 kilometers, 1 micron laser. You have the dimensions of the mirrors here, and the input laser power of 2 watts. Things that have been, they have been tested for Laser Pathfinder. So many of the things are already there, and there are new reflector meters of very high quality, of which we will hear tomorrow, that can be used. So by doing that, you can, through shot noise, without talking at all about protection from seismicity and all the rest, thermal protection and all that, just through shot noise, you get 10 to the minus 17, and you use it on the other 10 kilometers, and you get the nominal 10 to the minus 21 that you really need for this kind of studies. And so that's all I would have to say about it, and then probably we'll discuss about it tomorrow. Physics of the fiber, I mentioned it already. I will not go through it. I will not go also through the optical time domain reflectometry, which is essentially was invented by our colleagues, Mahmoud Farosian here, and his colleagues, and how with this you can obtain the parameters I just said about sensitivity, 10 to the minus 13. So only one thing I wanted to clarify, because it's not always very clear, but when you have, for instance, the gauge length, what you're essentially measuring through a phase change, you're measuring you see here the formula, Z, if you're at the point Z, you measure Z plus dz over 2, time plus dt, and minus the other side, and then minus the previous time, minus the time, okay? This essentially gives you either something which is the theta over theta t, or theta u over theta z, so the strain meter rate, or it can give you it can give you the spatial derivative of your particle velocity. Therefore, you can start associating it, for instance, to a geoform. And this is how the machine looks like it. You have numbers there, kilohertz, sensing points, dynamic ranges, and all that. I will not go through it. And you have two kinds of fibers. One is a simple fiber that you can deploy everywhere. And the other one is the one that is engineered. You hear about it. You have increased your points of reflection every, let's say, few meters. So that, and this gives you extra intensity in the reflection. So by using all that, you have this iconical plot where you see in that when you use the engineering DAS with, for instance, a gauge meter of 30 meters, you get for the displacement noise, for instance, for 1 hertz of the order of 10 to the minus 11 meters of the square root of hertz. So this is what, if you make the calculation, gives you the 10 to the minus 13 over square root of hertz relative strain. And the other thing you get is, of course, directionality. That we believe that will help you identify, if you have many deep mooncakes, as we were discussing all afternoon, probably could help you separate the directions. Now, taking this detector and accepting, let's say, only the intrinsic noise. I mean, don't take these comparisons as the final comparisons between detectors, because then that would be unfair. First of all, something that was said, I repeat it, you have a factor of 1,000,000, 10 to the 6, because of the moon. Jan has made a calculation. We made another one with our own parameters, different parameters of the moon, and that were in IPGP, and found the same numbers. So that's a good thing, at least at this level, the level of, let's say, simple parameterization of the response of the moon Actually, we even found 2 times 10 to the 6, so it's even better. But of course, we don't believe it. We keep the 10 to the 6. So that shows that, I mean, the first parameterization of what we believe. So the 10 to the 6 is what we believe it can be the multiplication factor that permits us to arrive to the 10 to the minus 21, as I said. And we also use the fact that we have, as I said, of the order between 400 and 1,000 sensors where we can stack them and can increase our sensibility. We also tried, and this you should not look at it because it's still very, very preliminary. The more sophisticated thing that it is, where you try to use, to use all the details of the moon structure, and we got results that are not yet very the same order. You see that they are pessimistic, as it is said. Around high frequencies, they start going down and they are not flat. But still, we put there the best we know of the moon, and we try to again to support the simple back of the envelope, let's call, calculation that gives us a factor of 1 million of increase. Having done this, we assume the 10 to the minus 13. And then you have here plots where we compare ourselves, for instance, to the plot up to the right, to the Earth low noise, is the blue line, flat blue line in the displacement, compared to Apollo, with even the horizontal of Apollo, because we're talking about horizontal displacements here. And you see that again, we are in a good situation. We are below that, get 1 or 2 orders of magnitude up to the 1 hertz. Some comparison with the other things that are in the market for the time being, the optical VBB, et cetera, et cetera. And again, I say that these things are not true comparisons. Is where we start from, where our noise level starts from. Certainly have to be studied in more depth to really be comparisons of sensitivity. Having done this, we can again compare our strain noise in our characteristic strain. And you see again that from the point of view, this is the light blue line. You see that, for instance, we can claim again on the intrinsic noise, and after having making stacking of the sensors, something like 5 10 to the minus 21 over square root of hertz, and compares well, and it is in this intermediate level frequencies that we're talking about from the time being, and starting, as I said, not from a bad point. Merger scenario, it was said by previously, how the big advantage of these detectors is exactly that also for the things that they will merge, or the things that will merge inside the Earth detectors, and of course some places where the thing merges in LISA, it's not us, but you also have things that are both LISA and the moon with different values, and you see the same logic, and you see again the same logic. We tried and tried again to play with this with different values, and you see the red line is the merger, and in between how many months, years, etc. We can see the event before it merges, and we put a 10-year limit as the limit that it is eternally in spiraling. So, because immediately afterwards, I will show you another plot. As it was said again, depends, of course, on the mass. The merger depends on the mass. It has been shown, so I don't want to show that. We made a study of the angular resolution you get. You have 3 ways to have point a place in the sky. One is comparing with the Earth detectors. The other two are if you are below a lunar month through the parallax of the moon, and below a year, beyond a year through the parallax of the sun. We used a 3-point triangulation, which is definitely a pessimistic one, because I'm sure that a more intelligent algorithm would give us better values. Nevertheless, you see many values of the type 10 to the minus 8 square degrees, which means that we might be able to isolate the galaxy without needing an electromagnetic accompaniment. So again, good progress here, needs more work, and I'm sure that we can use for the things we are studying. We can triangulate properly, both for electromagnetic accompaniment, but even without. This is our SNR as a function of mass and Z, to be compared to what we see between ET and Cosmic Explorer and LISA. And this is what I was telling. This is where we made our horizon with what we have, where you see the red plot is the plot of the lunar detector. You have in Pointillé, you have where you would see the merger, and in full is where you would, no, I'm sorry, yes, in Pointillé would be only the merger. With the full, it would be both the inspiraling and the merger. And you see that if effectively we cover, and certainly this plot, this horizon, which is enormous, will go down as long as we understand our errors, but at least it's a good start. I think that means that we're not very far, and indeed we cover between the two regions of the cosmos. Some limits. Special cases, double white dwarfs. Here we calculated, I don't even remember how, that we could have of the order of 2 or 3 per year for a galactic supernova. And we have two calculations, the one by Yan and the other by, Kinugawa. They are a bit different, but anyway, we might see double dwarfs together with, let's say, I don't know, other multi-messenger. That would be great news for dark energy. Intermediate black holes, you've heard a lot. I will not, we see the same things, that we will be seeing them. First of all, that we would be seeing, for instance, I have here their mergers and how they form, how we go from the stellar masses to the black holes at the center of the galaxy. We would be seeing it without electromagnetic, some of it we'll be seeing it without electromagnetic counterpart, and we wouldn't mind because we would be seeing the galaxy, and many more things that have been said. I don't want to spend more time, but obviously the intermediate black holes is the region where we could get a lot of information from this study. The other study that again, it's a little bit, this is high risk, high gain thing, is that if we have a core collapse supernova, again, and we would have, we could, I mean, this is studied by Svi, Piran and others, that we could have also, when we have a symmetric neutrino emission, we might also have gravitational waves exactly at the same frequencies, and that would be great. Gravitational wave background, I don't want to tire you. Again, the plot of and then all the things here, it's all the things that you might see. I mean, we'll hear more about it by Mary later on, but you would be able to see a lot of things happening behind or even just before the recombination war. Backgrounds. Have been a lot of discussion. I took too much time. I will not go through them. You know, the same plot that we have seen and the same issues of how we will try to understand them in order to be able to see all these gravitational waves. Again, the possible seismological goals need more study. We just, for the time being, we cite them, but certainly they are, I mean, I think the fact that you have a multisensorial network would be a great advantage, I think, for seismology. This is something that it is, I hope, that is something that will be a stable contribution anyway, independently of the other possibilities. Here again is the same thing with respect to what we have seen in Apollo and also places on Earth, underground places on Earth, as also Jan mentioned, where you have all the underground places and where you would need, again, you would be below the seismicity that you have there, and that you would need special things even there to be able to test your apparatus. Another interesting study is the one that led us to the conclusion that we need to be in a PSR, is the famous temperature disturbance that, for instance, but here it is at minus 60 degrees. It's not in, we have to repeat the study at the PSR. You see that as with respect to the first order strain, that is like this, let's say the perpendicular one, it is 10 to the minus 12. I'm sorry, the second order, it is 10 to the minus 12. It's okay, we can work with it. But the albedo and the cracks in the way the vibrations due to the changes of temperature are 10 to the minus 7. So they are, we cannot afford them. Certainly we need a permanently shadowed region. Certainly even there probably we need a multi-layer insulation. So again, this is with a very nice study done by Philippe together with his internship student Chevalier. So major challenges, and finishing. We have low mass, small volume, that's not a problem. Power, for the time being, a lot, 256 watt. But when we optimize the frequency, we will be sampling and all that, probably this will go down. Power is, as we said, most probably solar power close to a PSR. And why not, discussing the other day with Simone, I think DOE wants also to put back in circulation its RTGs, we see, the nuclear power. Data transfer 100 gigabits per day, we need to lower it down, storage again. And then deployment, the optimum contact, you understand, is a very important thing here, so that the fiber has an optimum contact. Rocket is one possibility, but optimum contact with the rocket seems a little bit difficult. Searching a little bit the literature, and we start working on that. There is a lot of activity. We'll hear about it tomorrow. Euromoon Mars, small moon rovers, Cube rover. For those of you that know the CubeSats, they are now Carnegie Mellon Astro Robotics. They make small, very small rovers where you have boxes you put on it, and also ISRO, why not? And of course, radiation protection and temperature, as we said. So in short, clear interdisciplinary content, interesting discovery potential, a lot of challenges. This is the place, up to now we did mostly the science, and a very interesting industrial societal future, because I think the word putting fibers on the moon is something that industrially is very, very important. And I have a bonus, but I think I spoke too much, so I will not say. We tried also, let me say that we tried also the acoustic, to use it as an acoustic antenna. And because of the ultra high energy cosmic rays, and their interest, these days they are very interesting. And it was a big effort to try to understand the formulations that existed and make compatible. And I think we managed to make compatible all the possible calculations of the acoustic sign that comes from a very high energy cosmic ray hitting directly the lunar ground. And then if we use the first idea, the one that by Volovic many years ago in the 70s, we get excellent results. We get, without any problem, the Auger surface. But if we use better data as we have now. We have very, very small grenades in parameter and 2 orders of magnitude less attenuation, more attenuation, I'm sorry, and we don't get too much. We don't get, that's where we are. We have to think a little bit about it. And that I finished. I'm sorry for taking time.
Questions for Stavros?
That's a nice idea. So I'm not sure I understand how the sensitivity would scale with the length of the fiber sensor. So you calculated for 10 kilometers. So what's the limitation? Why not going for 20 or 30 kilometers?
What is the limitation?
Yeah.
The limitation it is that you have 1%. First of all, is the deployment. The deployment of 10 kilometers is already big. With a rover is a big thing. But also, you have 1% coming back. So after some time, your light does not go back. You can have a higher, probably, and this is probably questions for my colleague tomorrow, you can have a higher power laser, but the 10 kilometers is more or less for the time being. But you've said the other day about even 40 kilometers these days, that you started to talk about 40 kilometers.
I mean, first of all, I think, the instrument was designed for lots of application on Earth, basically. So, but, in an optical system, there's a trade-off between what we call the spatial resolution and sensitivity. So the specification given in here is what we mostly use for general seismic applications, which is 10 meters. And usually you want to cover the entire wellbore. And typically these wellbores are, up to 10 kilometers. But we have done work up to 40 kilometers. And if you want to go to longer range, you can also trade off with the spatial resolution. For example, you could make your gauge length every 50 meters. And that can, as Stavros said, simplify lots of other parameters. But the goal on Earth has been always to get much higher spatial sampling for seismic, macroseismic flow applications. Whereas for these specific applications, we could definitely customize in terms of performance to improve it, but also reduce the power.
So my curiosity was if you had to optimize this for gravitational waves on the moon, how do you change your configuration? Longer, less spatial resolution?
Shall I?
Please.
Well, I mean, there are lots of ideas, but definitely if you want to measure things like gravitational strain, then certainly increasing the length would amplify the what you're measuring, because ultimately what you're measuring is the optical phase, and we have a short noise limited performance. So, but if you want to deploy it in such a way to do geoscience or measure seismic effects and imaging, then you need to create a sensing array. But ultimately the limitations would be getting to thermodynamic noise limitations of the fiber itself, and that's typically 10 to minus 15. And if you then say, okay, I don't need to go to such a high spatial resolution, reduce your detection bandwidth, then potentially you can get to lengths of 100 kilometers or even more. And then you multiply these numbers, then you're getting very close to this possibility of 10 to minus 21, but also be able to go to very low frequency, because unlike the other type of sensors where you have some mechanical transducer to create the displacement, you could really use the fiber as a relativistic media to be in the space and measure the change in the fabric of the space. So direct strain measurement, strain is a strain. So the few things we can discuss.
Yeah.
I'm learning as well, by the way.
Certainly, I mean, you can start being like ET triangular or make, I mean, it depends exactly on backgrounds and you know.
Okay.
Other.
Any question? If not, then let's thank Stavros again. And okay.
Karen is next. So this is not the last presentation before the discussion. In fact, after Karen, we have Jack Burns, but this is the last gravitational wave detector concept we are going to discuss now. So Karen, please.
Yeah, okay, well, hello again. I have this rare privilege of giving 2 talks today, but this one I'll make it fast. I know we are almost at the end of day. This is one of the third, let's say, proposals of a gravitational wave detector on the moon. This one is called Gravitational Wave Lunar Observatory for Cosmology. You can call it GLOC. You can call it GLOC, GLOC, whichever. I just call it GLOC. It's easier to pronounce instead of saying this full name again and again. But here we go. So just gonna take it back again. You know, we have various reasons on why we want to go to the moon. And I mean, of all the talks that we have also heard today, moon is like as if the solar system had given us this wonderful satellite where civilization eventually makes gravitational wave detector, right? It's almost sort of works out that way. It has this natural environment that you can create a large scale gravitational wave interferometer, just like the one we have outside right now, like the Virgo detector, right? The atmospheric pressure on the surface is comparable to the vacuum that Virgo has currently adapted. It's comparable to what LIGO has adapted. In fact, it's slightly better during sunrise sunset times at low frequencies. And I think this is like one of our selling point again and again, that at low frequency, we know moon is seismically much quieter than the Earth. A lot of challenges that we face in gravitational wave detection here on Earth, we would not face it on the moon. It only weakly interacts with environmental factors. Some of us who are actively working with the detectors here, it's pretty hard to make this kind of detectors work if there is an earthquake going on, or even if there is some form of other like seashore waves that let's say especially at the Louisiana detector, right? That even an earthquake in Australia can affect your detection that is happening at those regime. There is no human activities. When we make a joke that if we pass a truck through the Virgo detector, it's a glitch, but in reality, it is a glitch, right? These detectors are extremely sensitive. If you get any truck nearby these detectors, we most likely would have to restart the whole setup of getting locked again, because there is a human factor noise. That's why we need these detectors to be isolated locations, somewhat like how we are right now. On moon, we don't have to do that. This one point, I don't want to say it as a sort of negative against any space missions, but going to moon is some sort of a long-term investment, right? We are going to do science for sure. But it's not just going there for science. We are also building infrastructure on the moon that has a lot more implications than just saying that, oh, we are going to detect black holes there, right? It serves as a sort of a larger goal, just like going to South Pole to detect neutrinos also does in some fairness. It's also, if we are building infrastructure, we don't really have a timeline. Virgo detector, LIGO detectors have been running for a couple of decades, 2 decades for sure. They can run as is for a couple of more decades with maintenance, that kind of things we could expect on the moon as well, provided, of course, we are going to send astronauts to repair on the continuous basis. And we would not have been having any of this discussion today if it was not that the space agencies, the 2 leading space agencies in the world, are very seriously committed about the moon, as some sort of a flagship things that we would go next. So all these points is, and in the previous talk, I gave you all this list of nice decihertz concept. The moon concept of decihertz really work out because of this last point. That advantage only, specifically a moon-based gravitational wave astronomy has. So building up on these ideas, this came with a fun conversation with Avi Loeb at Harvard. And then this became eventually into a paper about this gravitational wave detector. At the time when we started written archive, I think it was the first in its sort of this advanced era that since we know we can detect gravitational waves. Again, the concept is old as Weber, but it's been there in this sort of a setup came very recently. It relies on feasible technologies. So it doesn't really need the moon in some sense to know the seismic activity as strictly as it would need for the other concepts, because we are still relying on an interferometric setup, right? We want to have test masses like how we have on Virgo detector. We want to have lasers. We want to take all of that up on moon. That's the challenge. How do we take so much things on the moon? But provided something of that works out, we know that if you put exactly this setup there as is, it is going to detect gravitational waves, right? But that's not an unknown in terms of the technology that is to be there. Slight modification from how Virgo detector is. This one is a triangular geometry, just adds a little more advantage, just like Einstein telescope has. What we envision is that either you have this landers or this end station that we see at point and point at the end, where you put the test masses here on Virgo itself. That needs to be temperature controlled, because moon, as Stavros's last plot showed, has this famous increase and decrease in temperature, not ideal to do kind of optics experiments that we need to do detect gravitational waves. We of course need to have them sort of shielded from cosmic ray exposure as well. So all those things need to be figured out. That figured out, this is the concept of the block. It was published in this journal, JCAP. This is a movie that a student from LIGO India and the LIGO India outreach director, they made about block. I'm just going to play this. Imagine in the background it is playing the Star Wars theme. It was perfect with the movie. But this is a nice 3D animation that they made by themselves in one of the very popular science outreach articles they wrote. Oh, it's not playing. Is it playing? It's not playing at the same rate that it's playing on my screen. That's a bummer. Blame it on Zoom. I don't know, those who are seeing on Zoom, can you see it by any chance playing? Or is it just playing on my, it's not, oh, okay, I promise to show this later to at least on the audience. But this is a very nice 3D animation of what this kind of, block kind of experiment would look like on the moon with actually some real images from the moon itself. Okay, now coming to more sort of technical points here. This is a new window in the gravitational wave spectrum, said again and again, but this one specifically here, so I've highlighted, again, this characteristic strain plot you see on the left. 3 regimes here. Space is where the LISA is, but there are also other concepts. There is ALIA, long back concept, extension of LISA. There is Hertz observatory that I showed in the previous talk. There's DESIGO. All of them have their peak in bucket, what we call, right? The peak sensitivity happens in this whole box, which is space. The detectors on the right are, once we know, Virgo, LIGO, Einstein telescope, Cosmic Explorer, all that we also discussed today. In between the two, in this Hertz, this sort of moon concept, can spike in. You can place LSGA, LGWA, Glock, all there, in some form. The Glock has 2 sensitivity curves. One assumes a conservative that we don't go below 1 Hertz with the current setup that we have. The other assumes we go up to 0.25 Hertz. It doesn't really reach 0.1 Hertz in the form of calculation we have done here. But again, these are very conceptual designs. We can improve, make better assumptions on what the suspension noise, etc. are, and may go even below this frequency. And we're going to have some talks tomorrow about that. Now, the notable point is the seismic noise in block would be, of course, have an advantage that the moon is quiet. You have a couple of orders of magnitude improvement as is if you would have taken a setup there. Of course, this is assuming that suspension noise, Newtonian noise, etc. don't overshadow what the improvement we get from seismic side. So use that noise curve and we do the standard astrophysics. This is a plot in a slightly different way than what we have seen today. This is the boundary of the circle, is the cosmic microwave background. So this is the entire observable universe. Every concentric shell in it is the volume of the universe that you can see for specific sources. So let's say if you pick binary black hole mergers, as LIGO has shown us that 30 plus 30 solar mass mergers happens at least 20 times every year in a cubic gigaparsec volume, right? We know that for a fact now, we have done enough observations. The circle that you see in the center, this very black dot, is the entire observable radius of LIGO and Virgo detector. And that is the farthest it has seen. All the influences in gravitational wave we have so far is within that circle. With a detector like Glock, the binary black hole merger, you can see up to 80% of the entire observable volume of the universe. You don't expect it to see, of course, binary black holes at redshift 80. This is a statement that this is the sensitivity that the detector can have. You put for a binary neutron star, you see about 70% neutron star black hole like the ones that we have detected. All these known sources that we know exist in gravitational wave astronomy, this is the distance detector on the moon can see versus the one on Earth. And so that is itself an unprecedented cosmological probe. And there are new sources that we don't think, we don't know how many of them exist. So we have to survey the universe as far as we can. One of them is, of course, the intermediate mass black hole. That kind of source also you see up to 75% of the entire observable volume of the universe. Intermediate mass ratio in spirals, one Alberto mentioned, that they are like not extreme mass ratio, but just slightly about mass ratio 1,000 or so. You can still see them up to a good like 30 to 40% volume of the universe, the entire observable volume. My favorite is the dark matter candidates, 0.5 solar mass black holes. You can see up to 30% of the observable volume of the universe. So this kind of a single instrument seeing everything from sub-solar mass black holes to this very heavy intermediate mass black hole. This is a huge mass range. A lot of astrophysics happens, but a single detector is able to see all of them. Right? So that is the stark advantage we have if we go on the moon. This is a more sort of a plot that we are used to seeing, the plot with the binary mass on the x-axis, the y-axis is the cosmological redshift, except this one is at a signal to noise ratio of 100. Those of us who are in data analysis, we have never reached that kind of sensitivity so far with Virgo or LIGO. Then SNR 100 would teach us a lot of astrophysical statements and also the test of general relativity. The black curve here is Glock, the sensitivity it has. You can see that below it would be Einstein telescope, below it would be Cosmic Explorer, and this small hurt you see is what LIGO Virgo is at this present stage. The LISA sensitivity curve is also seen, the Decius observatory is also in this dashed line. Everything that is under the Glock area default becomes a multi-band source. That if Glock sees that means the next detector on ground is also going to see. The overlap with LISA is also fairly substantial. You can go up to almost 100,000 solar masses overlap between a moon and a LISA-like detector. So plus, of course, everything that Einstein telescope or other future detectors on Earth will see. The next moving advantage, and I didn't really appreciate until starting this calculation, that because moon is a geocentric orbit, the sky localization is actually much better than a LISA has with a heliocentric orbit for a system such as stellar binaries that we see. Because one, as soon as let's say if a binary neutron star merges at redshift 2, the whole signal stays in the band, and that's actually at the low frequency part of it, for the entire time that the moon finishes one orbit around the Earth. So you got the gravitational wave, pretty much from different directions. Your sky localization has improved tremendously because of that. And that feature is common, of course, for all lunar gravitational wave concepts. If you take a binary black hole like 151226, which was this Christmas Day, Boxing Day event, a 10 plus 10 solar mass black hole, put that at redshift 2, which is, I guess, more than half the age of the universe. At that distance, it can be constrained to an arc-second square without having any electromagnetic counterpart for the fact that the signal stayed on the moon. And then, of course, it's eventually going to be measured by the ground network that already exists. We know the improvement that they do, plus you add moon, you add arc-second square, add redshift 2. That level in astronomy is pretty unheard. You open a new spectrum of dark sirens. That kind of sirens in the sense that we don't need light coming out of it, but you can use them as a marker of what the cosmic expansion history is, right? This is one of the long-standing troubles we have in modern cosmology, that the Hubble constant at nearby and farther away don't agree. This is a test that you could have throughout it, because we know that binary black holes do exist all the way from here to there. So that's a good test. The final one, and we're just talking about with Mike about this. This is a very exciting possibility of type 1a supernovae test. This is very specific to a detector on moon, whether it could be any of these concepts, that you have this long-term sensitivity at around 1 Hertz. Why long-term? Because you don't know how many sources exist and how far can you see. So you really want to, you don't want to just have a detector that runs for a year or 2 years and get only 1 or 2 sources, because the uncertainties that we are trying to gap is related to the type 1a supernova, which could be the progenitors. So their progenitors could be these white dwarf mergers. Type 1a supernova is what we use to measure the Hubble constant nearby. That measurement does not agree with cosmic microwave background. We don't know exactly why, but it could be, it needs a better calibration of what the mass of the progenitor was that eventually led to the type 1a that we see. That sort of astrophysics and fundamental cosmology you can do on moon. This one is particularly with clock that you can measure up to 2 gigaparsec, which is a very sizable radius that you need to find this kind of sources. So, I mean, this is a concept, of course. I mean, there are so many uncertainties I can add to this plan right now. But what I'm happy to see at least is people are responding. I mean, the fact that we, of course, have this wonderful workshop, and that is a testimony that, the community has advanced this concept, just not as a preprint or paper, but the entire community is coming together. We put this paper for snow mass. This is a decadal exercise that the particle physics community, especially in the US, does. This is where the flagship colliders are decided, what US is going to fund in particle physics. It's this huge exercise that happens. More than 70 people have sort of endorsed particle physics audience because of the kind of dark matter and dark energy, fundamental of physics aspects that you can do with an experiment on the moon. That's very promising to see. For the NASA Artemis, we submitted a proposal, of course, for the Artemis. This first few years is not about astronomy, doesn't rank that high, but at least the community got together and submitted. And we are going to have the same kind of submission also at the biological and physical sciences decadal. So all this is, within a scale of year, you can ask me, Jan or Stavros, just within a scale of year to see this kind of growth. And we have seen other future detectors too, and the time and hesitancy it takes to get over to start a new gravitational gap. And so this is super optimistic for at the time of pandemic, especially. It's coming in news, which I'm also very impressed because not that it is an indicator that we are going to get funded, but oops, they will not. Oh, okay, sorry. Takes a lag here. So multiple news media across the world has been covering the gravitational wave detector on the moon idea. The Forbes listed it as one of the 4 concepts NASA has to think seriously if they want to, do astronomy, like this cosmic dawn telescopes on the moon. It listed Glock as one of the ideas. There was this very nice article on this Science magazine Inverse. I love the title. It says the future of cosmology is 239,000 miles away, but closer than ever. 239,000. Of course, the distance to we have to the moon, and it's nice to equate cosmology with it. And of course, there are this other funny article saying that we could hunt gravitational wave if this wild idea takes off. And we could, in principle, hunt for gravitational wave if such wild idea does take off. So all in about, this is my first trip, by the way, to Italy. Yesterday was first evening, and I was walking in Pisa and I saw the moon. on the street. And I just suddenly thinking, wow, we can have something that we discuss here in a couple of decades. We place exactly there, and we can see every day that yes, there is a detector that we placed on the moon. So I think once it seems pretty impossible right now that we are going to take this whole Virgo kind of setup up on moon, but once we overcome the barrier of landing on the moon, which is the psychological barrier that we have right now, once we overcome that, a whole new horizon opens for our civilization to probe the fundamental laws of nature in a way that we have never tested before. So I guess on that note, thank you.
Thank you. A very inspiring vision on lunar gravitational wave detection. Let me, Andrea.
Yeah. So congratulations for your talk. We should learn from you also your communication skills. They're really very nice. Great. What about the possibility to detect a collision between giant planets or brown dwarfs? Because you are speaking, you presented the possibility for sub-solar masses detecting of events. Could be something achievable or not yet?
Yeah, that's a very interesting question. I mean, because most of these calculations that we use, we just happen to physically stop them at around 0.01 solar mass. It will be sort of interesting to interpolate them and just see, how because people have used LISA as an idea to hunt for exoplanets. And I don't see as a fundamental difference between using LISA versus a lunar experiment. So yeah, that would be interesting to check. Thank you. Yes. Yeah, I mean, yeah, everything within a couple of parsec, right, is what our target is. Yes. That would be interesting to see, yeah.
So thank you very much for the very nice talk. So did I see correctly that you can see white dwarf merger up to 2 gigaparsec?
Sorry, you mean with with Glock sensitivity?
Yeah.
Yes, we can see up to 2 gigaparsec, as is if we take Glock.
Because this is amazing.
Yeah.
In the sense that today we are using to calibrate supernovae in 19 Cepheids. So you could use really gravitational wave in a fantastic way to calibrate supernova type 1a. So it's you can detect a lot of.
Yeah. I was saying, I mean, this of all, I mean, there is so much interesting science we can do from moon, but this particular one, white dwarf merger, I think is like our crown jewel of all ideas, right? That this is very unique, that only moon can do.
Because Andrea did drive a work on this, but with the SIGO, and there, so the horizon was less than this one.
So the SIGO, if you see this curve, and so around here, if the white dwarf mergers happen, we get this sort of a slight advantage compared to the SIGO, just around that kind of range.
I think it depends also on the mass.
Yeah.
Sure. And the SNR, what we prefer. But I think this one was at SNR 8 or 4, one of the two.
I'm sorry, but it wasn't clear to me what is the advantage of using the moon here if you're just building something like a tree interferometer. You're basically building a small LISA, right? So what is the advantage of using the moon, apart from the fact that everybody wants to go to the moon now? So it's a sociological advantage, which is very important. But is there a scientific advantage in terms of cost? Will it be much cheaper than just a space mission?
Yeah, it would be cheaper to do a geocentric decihertz mission. But then once we do go here, I mean, this is only the first generation of experiment, right? And we have sent space missions since pre-Hubble era. And now we are at James Webb Space Telescope, great. But on moon, we have not done a fundamental physics experiment on this scale. And we don't know what particular advantage we would get, maybe from the size. I mean, eventually, instead of, I'm sorry, this could be provocative, but instead of, eventually we are not going to have land on Earth. Even in a case like TMT, we can't have it without controversy. So I think eventually we won't be able to make gravitational waves like this scales. So we need some other place.
I have a. Do you believe that this concept can be done without astronaut?
Can it be done with astronaut?
Oh, okay. It can. Okay. Is it possible to imagine a robotic mission, or is it something you can imagine maybe in an easier way if there is a permanent basis on the moon? Because clearly, if there is a permanent basis on the moon, I guess that this science can be put on the table. But if we do not have a permanent basis of the moon, which is something you can imagine within your retirement age, probably, but for a robotic mission, I think it might be more, much more challenging.
Yeah, and that's a great question. I just don't know how technologically it would be. I mean, ideally, it should be a robotic mission. We should have 3 landers at 3 different points that should make an interferometer. No, but the landers itself, if they are able to sustain what we want, the only thing we want is to protect the lasers and the test masses and the optics. So that's all the lander has to do, right? The lander, I mean, of course, there is a commissioning aspect, and Ian would get very mad at me if I say that it's a completely unhuman, like no humans would require, but.
Okay, because with the lander, what is not easy is to land. So, but you can imagine to use the resource of the moon, for example, to load or to make the mass of your damper. Okay, but at the end, this might be easy with people. Okay, but very challenging with robots.
Yeah, that's a fair point. Yeah, that's a fair point.
Yeah, I mean,
Sorry,
just first, just to mention, I mean, ET will end at 3 Hertz, its observation band. That's our goal, and it requires a 17-meter super attenuator at the moment. That's our current idea for suspension system. Of course, that's not even for ET the final word. Even there, we want to make it more compact. But the suspension requires these very, very fine, at the moment, very, very fine suspension fibers. Of course, you cannot shoot this to the moon. So somebody has to go there and would have to weld the fibers to the task masses and make the suspension in situ. From today's perspective, there's no way to avoid human beings doing that work. Commissioning in reality might potentially, in some sense at least, in other ways maybe not, but in some ways it might be considered easier because there are so few seismic disturbances at such a much lower level that the control requirements on your test masses is much reduced. So in that sense, this would help. But I mean, I think what I still like about all of this is that nobody has really carefully thought about how this could be realized. And I think doing that exercise to look into the technologies that you would have to realize, that exercise, I think, would tell us many, many things. Yeah. It might potentially even, even a showstopper might emerge. I don't know that. I don't think that they're really hard showstoppers actually in some sense, but I think it would be very good to look into this concept very, very carefully as a minimal exercise, because of course the science that it would produce is enormous.
So I was kind of curious about the half solar mass black holes as dark matter candidate, because I thought that the fraction of these type of candidates was very severely limited by the optical lensing experiment to less than like a few % of the total dark mass.
Yeah, no, that I mean, the only thing we are doing, I mean, we are doing this kind of a search right now. So we are in LIGO Virgo right now. We are searching for them, and the only, I mean, of course, it's an upper limit. right? That's the only statement we make. We don't make a claim of detection, but then we can constrain the fraction, of such sources might exist in. Let's say there are different flavors of dark matter. With this 0.1 solar mass kind of candidates. Oh yeah, that's I mean, yeah, and I think it's still, I mean, I can show the new Virgo LIGO paper. And so the advantage that we have is, that volume, what we are tracking them versus if we are tracking them at large scale. It may not pan out, of course. I mean, this is not the science case I would bet on to go on the moon, but just the sensitivity that exists. That's a statement.
Okay, maybe I think you raised your hand, but okay, very good. Yes, and without spacesuits, by the way. So that is the other point. So it's not quite so trivial. Because welding fibers is something that even I with my hands cannot do like that. It's a very so we should move on to Jack Burns, right?
Yeah.
Okay, thank you again, Karan. Okay, so Jack, I see you are ready to go. I think you might already be able to share your screen.
Yes, I'm trying to do that right now. Let's see if I can put that up. Are you seeing my screen now?
Yes, we do. Okay,
very good.
Very good.
All right, well, let me go ahead and get started then. Thank you for the invitation to present today. And I'm going to talk about a little something different, but technologically, I think related to gravitational wave detectors on the moon, and that is deployment of large radio telescopes, interferometers. As you see in the schematic here of a concept we're calling FarSide that I'll tell you a little bit about in just a few minutes. I think there's an overlap in some of the techniques we might use for robotic deployment, as well as an overlap just in listening to Karen's talk here just a moment ago about cosmology. So what I'm going to do is I'm going to build a story here of the development of radio astronomy on the moon, a kind of roadmap, if you will, for that development. And that was laid out in part in a paper in the Planetary Sciences Journal that's listed at the bottom of the slide here, published just a few months ago, for those that might like to read a little bit more. So let me start by just mentioning my colleagues, my collaborators. Our group is funded in several different ways by NASA. And in particular, we're funded by NASA SSERVI, the Solar System Exploration Research Virtual Institute. Our team is called NEST, the Network for Exploration Space Science. I list a number of my collaborators here, all very important in the work I'm going to be talking about. All right, so let me get started. We're very excited about the first NASA-funded radio telescope that is going to land on the moon in just a few months. It is going to be delivered to the moon by the Intuitive Machines company out of Houston, their Nova C lander. This is part of NASA's new program called the Commercial Lunar Payload Services. I'll talk more about that in just a moment. Our instrument is called ROLSES, and it's designed really to probe the photoelectron sheath in the vicinity of the surface of the moon, the local ionosphere, if you will. And this effort is led by my colleague, Bob McDowell at NASA Goddard. As I mentioned, this instrument, it's pretty simple. It's just two dipole antennas, one dipole 1 meter above the surface and a cross dipole that's 3 meters above the surface. As I say, it's mainly for plasma observations. But this mission, which is going to be on the near side to begin with, is going to allow us to set the stage for some of the more interesting far side cosmological observations that we want to do by measuring reflections off of the lunar subsurface and allow us to look at electromagnetic interactions with the dielectric material in the subsurface, and also measure the galactic spectrum between 1 and 30 megahertz with some degree of fidelity that we need to understand that foreground for cosmological observations. So this is the launch is expected in the first quarter of 2022. So this program that's going to deliver roles to the surface, as I mentioned before, is called the Commercial Lunar Payload Services, or CLPS for short. Karen mentioned that just a few minutes ago. It is a game changer for us wanting to do science from the moon because it provides regular access to the moon, 2 landers per year. And in fact, next year in 2022, there'll be 3 landers that are going to go to the moon. And it provides us with an unparalleled opportunity, not only to the near side, but also to the far side of the moon. It's going to be not just a one-shot kind of thing, but will be multiple landers. So we can envision, for example, putting initial instruments on the surface of the moon, learning from those observations, doing some retooling and upgrading, and then flying again in a few years, or at least proposing to fly. Very much more like what we do on ground-based telescopes. And also the costs are comparatively low because NASA provides the rocket flight, the launch costs, the lander, the power, the communications. And so for a few $1 million, we can do powerful radio frequency hydrogen cosmology observations. The far side is a driver for us because it is uniquely radio quiet. The several thousand kilometers of rock block off the radio frequency interference from the Earth. The Earth is limiting us at these low frequencies below the FM band because of the ionosphere, both refraction and absorption. And then lastly, also the environment on the moon is very important because it's dry and stable, unlike the moisture-filled soil, which changes the dielectric properties from time to time. So our first mission to the far side is called Lucy Dapper. And the Lucy part of the mission is already manifested to go to the Schrodinger impact basin, which is in the southern hemisphere of the moon in 2025. And it's going to carry these Stacer dipole antennas that you see stretched out over here. Those will make observations between 10 and 45 megahertz. And then we're discussing with NASA and actually the Department of Energy in a second antenna, a patch antenna, that will give us access over a wider frequency. Let me play just a short clip here, actually from a planetarium show that we're constructing at the University of Colorado called Forward to the Moon. And it's just a quick little clip about this mission.
The Lucy Dapper instrument on one of the CLPS landers will carry out initial tests using a small radio telescope. This will measure the low-frequency radio environment on the lunar surface and make the first cosmological measurements from the moon.
I hope you were able to hear the audio on that. I'm just testing that right now.
Yes.
Yes.
Yes, we are hearing this. Yes.
Yes, you did. Good. Thank you. Little sort of overly dramatic from our professional narrator here on this particular mission, and the strange curvature that you see here is also because we're looking at a planetarium show. So why are we going to far side? What we're doing is cosmology and to map the evolution of the universe. So down below, what you see here is a schematic of, in fact, the evolution of the universe from the Big Bang on the left to today's universe on the right. Our first observations of the universe are with the cosmic microwave background at the epoch of recombination. And of course, you get these pioneering satellites like COBE and Planck have given us our first views of the early universe. At this time of recombination, of course, you have electrons, protons combining to produce the first neutral hydrogen atoms, and the universe becomes transparent at that point. This is the beginning of what we call the cosmic dark ages. So no stars, no galaxies yet, but there are halos of dark matter and neutral hydrogen, which are collapsing and will produce those first stars. But the universe, I just mentioned again, the intergalactic medium is filled with neutral hydrogen. A little bit later, about 300 million years or so after the Big Bang of that order, the first stars form according to models. They'll be of order 100 times the mass of the sun. Those first stars will turn on, they have ultraviolet light that will ionize the surrounding neutral hydrogen and produce these little bubbles that you see here in purple. This is ionized H2 regions. Eventually, more of these stars turn on. They begin to ionize the surrounding intergalactic medium. And there's the last phase transition of the universe going from an all neutral to an all ionized intergalactic medium. So that's the story. That's the theory. The problem is we lack observations in this fundamental time period, the cosmic dark ages into the early stages of the cosmic dawn. Hubble and James Webb and some of these powerful radio telescopes we have on the ground, they can stick their toe into the waters of cosmic dawn, but not the very first generation of stars, because those stars are simply too faint. So how do we sample this time period? Well, remember, we said that the universe is filled with neutral hydrogen, and neutral hydrogen has a hyperfine transition in its ground state that produces radio emission, which when we observed is redshifted, stretched to frequencies below 50 to 100 megahertz, so below the FM band. So that's what we want to use to probe. In fact, it's the only way really there is to probe this particular time period in the early universe. It's a powerful time period because it's relatively simple, particularly the dark ages being absence of stars and galaxies, to probe not only to test our fundamental models of cosmology, but also to look for new physics, particularly associated with dark matter. So we know there's various models of dark matter, annihilation and decay. Models show that this will imprint on the signal that we get from the 21 centimeter global or all sky observations that we would make. Recently, there have been models suggesting non-gravitational interaction between partially charged dark matter and baryons. Some examples of those models are shown in the upper left here. This is the brightness temperature against the CMB. Think of this as radio power observed as a function of frequency. And the different models show the impact of dark matter, baryon interactions. So the dashed lines show without those interactions, and the solid lines show that this deepens the absorption trough that is expected here. And so right here, you can see a potential probe of dark matter. Another one is if dark matter has different flavors, if warm dark matter exists, as has been proposed to explain the lack of dwarf galaxies around some larger galaxies. You see here, for example, a difference between within body simulations of a CDM universe and a warm dark matter, that is a cold and a warm dark matter universe. Because of free streaming of gas in the warm dark matter, there's less of the compact structure that is produced. That directly impacts also the neutral hydrogen signal. So just very briefly, you can get a flavor of the kinds of new physics, particularly with dark matter, that we can probe at these radio frequencies. So that's our first few simple telescopes, single dipole antennas. Let me talk next about an array of radio telescopes, which we call FARSIDE. This is an acronym. It's used to probe the dark ages and exoplanets. This is a study that NASA Astrophysics funded us to do several years ago. We partnered with JPL and Caltech and have submitted this to the decadal survey, and we're eagerly awaiting the results from that decadal survey. But what you can see here is a mid-sized lander, in this case, Blue Origin Blue Moon lander. Blue Origin has been one of our partners in this. And then these single axle rovers from JPL. And what we do is very simply pull out these tethers, and embedded in the tethers are our dipole antennas, electronics, power, and communications. Here, just showing you that with this single lander that we have here, that we can bring the entire array to the surface, 4 of these single axle rovers. Total mass is about 1.5 metric tons. The lander itself, according to Blue Origin, can deliver about 5 metric tons or more. So it's possible in a single landing to then robotically deploy what we need for the entire array for Farside. Just a little bit more about the mission architecture. So these 4 single axle rovers will spread out in a spiral-like pattern. This gives us good, what's called UV coverage. This is good synthetic aperture for doing the radio interferometry over a 10-kilometer total diameter, so similar in size to what we heard of some of the concepts for the gravitational wave detectors. The lander serves as our base station, our electronics, our FX correlator, our comms, and power are all within this package. And we are going to be using some low temperature electronics pioneered by JPL to be able to operate both during the day and the night. So just a little bit more about how we pack these things together. Using the study that we've done so far, you can see that we can put these 4 large single axle rovers on the top, and then these are spring loaded so that after we land, they pop out, and then we lower them with the tether to the surface of the moon, as you saw. So what's interesting about these tethers is, in addition to embedding these antennas that are tens of meters in length in our receiver boxes as well, we also will embed some fiber optics for our communications and power. So we've been collaborating with folks at Caltech to also look at using that fiber optics, as we heard a little bit earlier, for a kind of distributed acoustic sensing array as well. It could be so there could be multiple applications we could make with this deployment. All right, just a little bit more about our rovers. They're pretty large. You can see that they're close to 2.5 meters, even larger than Elon Musk and his ego here that you see all dressed up and ready to party. And you can see our spool on here. This is both the tether, our flattened electronics, our preamps, and stereo cameras for teleoperation on the surface. We've experimented at JPL with deploying a polyamide tether. And let me show you a little bit of that experiment. I'm going to fast forward this a little bit from a few years ago. Shows you how this is sped up, but it shows you how one can teleoperate and deploy a tether in this particular experiment. The rovers are pretty high technology readiness level in NASA parlance. This is TRL 6 and above. So these are ready to move forward. None of the technology that we're proposing here is in need of advanced development. This technology is all within sight of what we have available today. So let me see if I can advance here. We also did another interesting experiment actually in space a few years ago, and that is we used another rover, a K-10 rover at the NASA Ames Research Center. My students and I built a deployer for the polyamide film. And then you see astronaut Luca Parmentano from Italy here operating our laptop that we provided with control software for navigation. There's a LiDAR on board here, so he can navigate around any obstacles. And so he directly deployed this with no, so it was in direct communications with our control center at NASA Ames. So this was the first demonstration of teleoperation using a kind of deployment mechanism that we would like to do on the moon. So obviously this is first operation from space, but it was on the Earth. We feel that this can easily be done from the moon. This work that we're doing, speaking of teleoperation, is one that is made for a wonderful student project. I have undergraduate and graduate students. We have built our own rover, mechanical arm camera that you see here. We're calling this the Armstrong rover. It has a very simple game controller that we use here. We have designed some specialty software that operates. The stereo camera here allows us to put a head-mounted display on and to use both virtual and augmented reality, as you'll see with one of my students here, the camera deployment. And you can see that the way this is operated here is from the head-mounted display following this along. So this is very useful in a next generation of how we would operate. To take this one step further, we've brought this rover into the virtual environment and developed a digital twin inside a game engine, and then able to put this rover on the surface of the moon. We use the identical controlling software for the real rover with this virtual reality version. And we're using this for rapid prototyping and also for problem solving, getting into situations on the moon where maybe things get stuck, and we look to get this all unjammed. All right, let me move on to the last part of our roadmap, and that is sort of the ultimate array for cosmology, a 100,000 dipole antenna array for dark ages 21 centimeter cosmology. We're calling this FARView. Recently, NASA's NIAC program, the NASA Innovative Advanced Concepts, chose this for a study. And we're working with a company in Houston called Lunar Resources, both on the deployment of the array, but as we also heard some questions a little bit ago, is to doing in situ manufacturing of the antenna components and even the solar panels using a molten regolith electrolysis approach to do this. Let me show you just a quick video here that illustrates the basic technique, both the deployment and in particular the in situ manufacturing.
FARView is a next-generation astrophysics radio observatory built on the moon's far side. The only radio-quiet place within the inner solar system to study the earliest stages of evolution of the universe. The Lunar Observatory will be built from Lunar Resources and constructed directly on the surface of the moon using space industrial equipment sent from Earth. The required materials will be extracted by Lunar Resources manufacturing technologies from the lunar regolith. A truck rover then delivers the extracted raw metals to the construction site for the fabrication of antenna elements, solar cells, electrical transmission cables, and batteries. The observatory's antenna array and power grid is then assembled directly onto the surface of the Moon, utilizing Lunar Resources' space manufacturing technologies and its partners' intelligent lunar rovers. Farview is estimated to be a 10 by 10 kilometer observatory with 100,000 dipole antennas and will take less than 4 years to be constructed. The Lunar Observatory will explore the origins of the first structures in the universe, opening new science windows into low-frequency radio astronomy, seeking to uncover new physics and test standard cosmological models, and enable new science in heliophysics and planetary science. Farview will be one of the most powerful radio observatories for learning about our universe.
So just in terms of timeframes, far side, we're looking at deployment later this decade. Farview, though, is something more for the 2030s that has the dual purpose of advancing the ability to live off the land, if you will, on the moon and deploy large scientific instruments. So in conclusion, let me just say the CLIPS program, as I mentioned before, really is a new paradigm, getting us to the moon, getting us with multiple small missions that then lead us to these larger ones. We've been encouraged now with these intermediate size landers that SpaceX and that the Blue Origin are producing to look bigger, to look at not just instruments that are a few tens of kilograms, but are metric tons, so that we can begin this era of big science from the moon. So with that, I will stop there and be happy to take some questions.
Thank you, Jack. That was amazing. As a scientist, I hate to say that your lunar exploration technologies were stealing the show. So the radio telescope. Well, anyway, also that one was amazing. So Stavros, please.
Yeah, I also have to try to close my mouth before I be able to formulate something. By wow. What about the TRL of this rover of the tether rover? Is it close enough to space?
It is. These Axel rovers that you see behind me here,
yes,
on the other side,
yeah.
These are at this TRL 6 level, 6 to 7. So JPL has been working on these for a number of years. They have a number of mission concept designs that have put forward. So this is ready for an advance, and we believe could fly in just the next few years. So in doing our design study, particularly of Farside, our guiding principle, and JPL kept us to this, is no magic. That is, no technology that really doesn't exist today that we can pull together and fly. And I think we were able to demonstrate that and keep within the budget of the astrophysics probe class mission, which is about $1 billion.
Thank you. That's great.
Similarly, let me just mention when we're talking about the in situ manufacturing, the electrolysis technique, that technology also is well developed. The extraction of the aluminum from the lunar surface is the same process that's used on the Earth. So that's well in hand. And then the electrolysis for the plating of the antennas on the lunar surface makes great advantage of the high vacuum, as was stated earlier here in the conference, of the moon. And that also is at a TRL 4 to 5 level right now. And the company Lunar Resources is slated to test this with some space missions coming up in the next few years.
Hello, I am Philippe Lognonet. So I understand that we might have the pleasure to fly together on Schrödinger, because I am in the FSS payload. So my question is simple. So do you believe that LUCE has the sensitivity to detect the radio burst of hypervelocity impact nearby?
Sorry, the bursts of what nearby?
Okay, so when you have a hypervelocity impact of a micrometeorite, I think this is generating 20 gigahertz burst of radio wave. So therefore, do you believe that you will have the possibility to detect that? Because if yes, then we will have two payload instruments. So we will have two instruments on the payload to detect that impact.
Yes, we've looked at that. That's outside of my area of expertise, but my colleagues at Goddard and Berkeley have looked at that both for Rolls's and for Lucy. That is part of the science agenda. So we believe that below a megahertz in particular, that we'll be able to detect the radio signals from these micrometeorite impacts onto the lander and the on the antennas. These, of course, are collections of micrometeorites. So yes, I do think there's an opportunity to then do some comparison. This is something that has been suggested for years, but we've not had the opportunity to fly both of these kind of instruments to detect the micrometeorites and dust.
So hi, this is Karan, and thank you. This was an incredible talk, and it was just real wow. I had perhaps sort of now maybe gravitational wave question. So there is now this interest for pulsar timing array with radio telescopes around millihertz range. Is that something that like measuring pulsars, is that something at all possible with if not with FarView, but some other radio observatory on the moon?
It might be, although the frequencies that we're looking at below 100 megahertz means the dispersion from the pulsars is going to be very high. But interestingly, LOFAR in Europe recently detected some fast radio bursts, which also suffer from dispersion at around 150 megahertz or so. So I think it would be at least worth thinking a little bit more about, but it could be challenging.
Okay, all right, well, thank you.
Any other questions? Thank you again, Jacques. It was a great talk. Thank you.
Thank you.
So now we finish this exciting day with Mary Sechelariadou, who is a professor, a well-known gravitational theoretical physicist, but also the head of the gravitational section of EPS. So, Mary, please.
Yeah. Thank you very much for the invitation. I'm sorry I cannot be in person. I'm right now actually at Caltech. So let me share my screen. Okay, I believe it's a bit different talk than what you had so far. So I would like to somehow give you an update on the stochastic gravitational wave background. And we're still searching for that. And I would like to highlight what the implications are for astrophysics, high energy physics, and the early universe. So as you know, the universe is full with electromagnetic radiation, which is the relic photons of the Big Bang. In the same way, we expect that the universe is going to be filled with gravitational waves, which are the product of some kind of processes in the early universe, like phase transitions, topological defects, or inflation. And in the addition, there is a background, which is the outcome of gravitational waves coming from astrophysical sources, which are either very far away or very weak, and therefore, with the detectors we have today, we cannot separate them. Now, the energy density of gravitational waves goes like the square of the time derivative of the amplitude, and usually it is expressed in terms of a dimensionless quantity, this omega GW, which goes like the energy density of gravitational waves in a logarithmic interval of frequency and normalized by the critical energy density. Now, if we try to detect the stochastic gravitational wave background using one detector, then it is impossible because the noise is much bigger than the strain. As you can see here, I work in Fourier space, I is my detector. And therefore, the only way to be able to detect a stochastic gravitational wave background is if we try to correlate the output of two detectors, I and J. So H is the strain and N is the noise in your detector. Now, the SNR grows slowly over time. As you can see, it goes like the square root of the observational time. Now, how are we going to search for a stochastic gravitational wave background? We are going to build this estimator here, which is given in terms of the Fourier transform of the strain time series in the detection I, starting at the time t. This gamma ij here, as you can see, is the overlap reduction function, which is going to capture all the geometric quantities of our interferometer. S0 is the normalization, and t is the time that you do your observation. Assuming this background to be isotropic, Gaussian, stationary, and apolarized, then it is given by a single spectral density here, which is defined in terms of the two-point correlator of your amplitude in this way, and the relation between the spectral, the single power spectral density S and the omega GW, it is given here. Now, if you assume that the gravitational wave signal and the intrinsic noise are uncorrelated, then this estimator which you have built is the omega GW with a contribution from the correlated noise of your detectors. In the absence of this such a noise, then this C hat is an estimator of the energy density of gravitational waves. But what if there is a correlated noise? And we have such a case, the Schumann resonances, which are very low frequency resonances in the global electromagnetic field of the Earth. And then you can see this kind of peaks here at frequency 8, at frequency 12, and so on. And you can see them as well that they appear in the data near the Virgo site, actually near where you are located right now. And you can see the 5 harmonics.
Mary, stop 1 minute because we've lost you from the main screen. We have you in our, every one of us have you on screen, but we've lost you in the main screen. Is it, wait a minute, just a minute.
Wait.
Okay. Come back. Okay. Coming back. Yes, can you talk?
Yes, I can talk. So you want me?
Fine. Now we have you. Good. Go on, please.
Okay. So this estimator, which we built before, is going to give the omega GW plus a magnetic contribution. So how can when we're going to have a detection, how we know that's a real one and is not a contamination? So not long back, we just proposed a novel approach in order to try to search for this kind of contamination, to separate it from the real kind of detection. So here are the data from the magnetometers at the sites I and J, which are given in terms of the correlated magnetic power spectral density, M. So what you are going to have, then a correlated noise is going to be transferred to the detectors from the magnetic field, which is expressed in terms of the transfer function T. Here, this kappa and this beta are quantities which we know from the second observing run of LIGO Virgo. So here is the overall magnetic contribution which we are going to have, and we have to take into account. So during the third observing run, we use for first time the 3 detectors, the 2 LIGO and the Virgo one. This is very helpful because it improves the high frequency sensitivity, and we can have the possibility, as I will show in a minute, to distinguish between different polarizations, so beyond standard GR theories. So we observed the amplitude, the strain, we cross-correlate, and then we have the optimal combination to get the estimator I was talking before. So then we fit the models to the O3 data using a kind of hybrid frequentist and Bayesian approach. So here you can see the multi-baseline Gaussian likelihood. So here is the C hat and the sigma are what you are going to have from the LIGO Virgo data, and you are going to fit them your model for the omega GW with the parameters theta. So by doing that, we found that the Gaussian noise is preferred over correlated magnetic noise, and the Gaussian noise is preferred over correlated magnetic noise and a power law gravitational wave background. Now, there are two parameters that we have to fix in our model. Usually we take that the energy density of gravitational waves goes like a power law frequency dependence, and the value of this power law depends what is the source. Is it cosmological? Is zero? If it is compact binary coalescence, it's 2/3. You take the inspired phase, you take the quadruple formula, and immediately you get that is 2/3. So we're able to put constraints depending what is the value of alpha, if we're talking for inflation, for instance, of cosmic strings, or if we're talking for CBCs. And here is the constraints that we put from the non-observation of, from a non-detection of a stochastic gravitational wave background. Now, in addition, we're able to put constraints in beyond GR models. We cannot do it by just using the transient gravitational wave signals, because in order to do it, we need at least 6 detectors, and the LIGO detectors have almost the same orientation, and therefore they count as 1. So we cannot search for 6 different polarization modes. So we can propose the Bayesian method to detect and characterize the polarization with gravitational wave background, which has been used during the O2 and the O3 runs, and up to now we have found no evidence for a non-GR polarization. So we have consistency with the predictions of Einstein's theory of general relativity. So let me take the compact binary coalescence. As I told you, the frequency dependence is like 2/3. So here in this plot, you see the 90% credible bands for the omega GW from BNS, which is the red one, and from BBH, which is the green one. At the time, we did not have a confident NSBH kind of candidate. That's why you see the upper limit. In the right-hand side, what we do is we calculate with the measures that we have from the LIGO Virgo detections, the BNS and BBH contribution to the omega GW, which you can see here. And if you calculate an omega GW, which is tangent in one of these sensitivity curves of your detector, that means you have made an observation at the 2 sigma level. There has not been an observation, so at the best frequency that our interferometer works, which means 25 Hz, this is the constraint that we have put. Now, I would like to make a comment here. One should not be surprised that we have not detected yet a stochastic gravitational wave background, just to mention that is much smaller than the one you get from the CMB, which is about 10 to the minus 5. So it is indeed normal that we have not detected yet. It's pretty hard. Now, the question is, how does the omega GW from compact binary coalescence is going to depend on what is the astrophysical model you have deployed for the mass and spin distribution of your black holes. So we did this exercise a couple of years back, and what you can see here is that by taking something like 10,000 different models of black hole mass distribution, the spin does not play a big role. We have found that the omega GW changed by almost 2 orders of magnitude, which means that the day that we make a detection, we'll be able to say something about the astrophysics behind the binary black holes. Now, moving to what we can learn about beyond the standard model particle physics, let me take the example of cosmic strings. The universe evolves, it undergoes phase transitions, the symmetries are spontaneously broken. Topological defects may appear as relics of the previous, more symmetric phase of the universe. One of them is these one-dimensional objects that we call them cosmic strings. They evolve, they intersect, they create loops. At this intersection, you are going to have a discontinuity, a kink which is going to be formed. Kinks, they collide with each other. And in addition, you have points on the string that instantaneously it moves at the speed of light, which call them cusps. Kinks and cusps are the points from where you are going to have the most of gravitational waves emission. So now it depends again on what model you are going to consider. So you have pretty complicated numerical simulations, which are going to tell you the distribution of loops of a given size. How many loops I have of a given size, which is the number of kings, which is the number of castles that I have circled here in blue. A simulation is going to give you that. And then once you know that, the only free parameter you have is the tension of the string. The tension of the string is going to give you actually the time at which these objects were formed. So this is important for cosmological models. Usually these objects appear after infusion. So here we have different models that we have considered. So the main mechanism is going to be the cusps, unless you have many kings, and then the kings are going to win. So in the last third observing run, we have considered these four kind of different models, and we try to put constraints. What is the tension of the string which is excluded? In other words, when these objects could have been formed, given that we do not see them in the stochastic background. And I'm glad to say that the constraints that we put from the stochastic like of Virgo asserts are the strongest ones which exist in the literature for 3 out of these 4 models. And if you would like to have a comparison, what does this mean when I say 10 to the minus 6, that corresponds to strings formed at the GATT scale, and so on. Now, if we move to LISA, with LISA, we're able to go even better and put constraints on strings down 10 to the minus 17. However, in order to do this calculation, that was a LISA collaboration paper, we took into account only the instrumental nodes. But more recently, we explored again this thing, saying that what is going to happen with LISA is we'll be able to have a huge contribution from an astrophysical background from compact binary coalescence. In addition, is going to be a galactic foreground from the white dwarfs. So these are going to contaminate somehow your signal. By doing this exercise, we have found that actually we cannot go better than 10 to the minus 16, 10 to the minus 15. In other words, objects that have been formed closer to us, let's say. And because you have a decontamination, this is the yellow thing, the confusion noise, which comes from the galactic foreground from white dwarf binaries. Now, going again to beyond the standard model particle physics, again, as the universe expands, it goes under phase transitions. You're going to have bubbles. You are going to bubble nucleation that they are going to bring you from the false vacuum to the true vacuum. Now, these bubbles are going to collide, and during this process, they are going to form gravitational waves. You need a second order phase transition. If you have a first order phase transition, then it goes adiabatically, and then you do not have a kind of quadruple contribution to the energy momentum tensor. So you need a first order phase transition. So then the stochastic background that you will get, remember I said that for CBCs goes like 2/3. In the case of phase transition, is the broken power law with a peak frequency, which is determined by the temperature of the phase transition. If the temperature is between 10 to the 7, 10 to the 9 GeV, which is not accessible at LHC, then we get a stochastic background within the LIGO Virgo frequency band. Here in these examples, you can see that depending on the model of phase transition, which means the strength and the inverse duration of the phase transition, you can be within actually the detectability of the LIGO Virgo. So we consider the O1, O2, O3 data in the stochastic search, and we try to search for such a signal. There is no evidence that, of the phase transition, and we could put some constraint in the contribution of the stochastic background from first order phase transitions, which means now that one can go back, particle physicists now can do that, and can go and put constraints in their models that lead to the production of these processes. Now, there is an interesting actually aspect as well that one can consider about the early universe is about the possibility of population of 3 stars. These are hypothetical stars that could have been formed at the very early universe, so have very low metallicity and very big redshift. If you try to look for them, as you can see here, look here, the green is population 1, population 2, and here you have the red one for population 3. You cannot see them with 2G detectors because this they took place very early in the universe. Okay, we have tried to see whether by taking simulations, the Star Trek simulation that gives the distribution of population 1, 2, and 3 stars. And what we have found is the population 3, as you can see, are going to be completely wiped out from the population 1 and 2 stars. In order to uncover them, you have to look at the residual backgrounds. In other words, what it remains when you have subtracted all the individually detected major events. And in order to achieve that, you need Einstein telescope plus 2 cosmic explorers. You have only Einstein telescope by itself you cannot do. And why here it's going to work? You can see that the total population 1 and 2 is here. The total population 3 is here, but the residual one, as you can see, of population 1 and 2 goes down, but the population 3 goes up. Why is that? Because the subtraction methods are less efficient to detect the high frequency and low, the high redshift and low frequency population 3 compact binaries. And therefore, given that it's more difficult in order to resolve the population 3 stars, that means that they will remain, and therefore they are going to give a larger contribution to the cosmic, to the CBC background that is going to be remain. How are you going to look for that? You cannot look anymore for the 2/3. Why you cannot look with the 2/3? Because the 2/3 is the characteristic of the inspirer. Here we see them during the merger and the rip down. So the 2/3 is not going to work. So we did some Bayesian statistics, and for all the models that we consider, as we can see, whichever of the models we consider, it is favorable with respect to the 2/3. So you cannot set with the 2/3. In addition, we found a relationship between the peak frequency and the redshift to total mass, which means that the day I will be able to make a detection of population stars, and I'm able to estimate the peak frequency, I could get some important information about the average redshift to total mass. Now, what about, again, going back about what we can get about early universe, then they could, we expect that a second order perturbation theory from scalar perturbations is going to lead to the formation of a strong stochastic gravitational wave background, which is going to be accompanied by primordial black hole formation. So we try to put some upper limits on the amplitude of the power spectrum and the fraction of the dark matter in terms of ultra-light primordial black holes. We're interested in the LIGO-Virgo band, which means that we can put constraints on primordial black hole with mass smaller than 10 to the 16 grams. So here is the peak curvature power spectrum that usually we consider in these cases, that depends on 3 quantities: the power of the peak, the width of the peak delta, and the K star, which is the position of the peak. So here we saw the comparison of the exclusion kind of region for the integrated power of the peak, for the LIGO-Virgo, LIGO design sensitivity, Einstein telescope, and you can see that even now, which are much better than the constraint from Big Bang nucleosynthesis or the CMB. Still, the constraint, these green lines, which come from primordial black hole formation, are stronger, but particularly with Einstein telescope, we'll be able to beat this constraint for a pretty good region of the position of the peak. So it's very interesting that you know, we can put constraints in many things related to the early universe. Another thing I would like very briefly to say about the universe is, as we know, we live in a universe where there is an asymmetry between matter and antimatter. So if we go back to the Sakharov criteria, we need that at some point we need parity violation. If we are able to search and find the parity violation, then you know that the origin is more cosmological, not astrophysical. And in addition, we'll be able to put some constraint on the theory that led to this parity violation. So there have been some studies in Chen-Simon's gravitational theory about axion inflation, and more recently, we tried to put some constraints in the case of the turbulence in the primordial plasma. So now what you have, remember when I said before, in order to find the stochastic background, we correlate the output of 2 detectors. Now this correlation, we're going to have the right and left polarized modes, which are given from the stock parameters I and V. The V is equal to 0 in the case that you have unpolarized gravitational wave background. So the omega ZW I was talking before is going to have a contribution from the polarization degree, which is 0 if it's unpolarized, your background plus or minus one is fully left on right polarization. We searched in the most recent data of the LIGO Virgo runs searches. We found no evidence for polarization. And what is interesting is we found that there are two relevant stochastic gravitational wave background upper limit. One, which is going to confirm the presence of a polarized signal, and the other one, which is going to give us confidence in order to be able to estimate. So all that are going to be used as well. Whatever I said today are going to be used as well, and much more for a cosmological implication study of the O4 arm of the LIGO Virgo Kagra collaboration. Now, up to now, I told you that the stochastic background can have different kinds of contribution from CBCs, from cosmological origin, for phase transition. And the question that one can ask, if I detect it more, if I know that it's not contaminated, how can I know where does it come from? So we did this analysis like a year ago, and unfortunately, we found that with current detectors, we're unable to separate astrophysical from cosmological sources. Then we took the standard configuration of 3G detectors, so two cosmic explorers at the LIGO sites and one Virgo and one SN telescope in the Virgo site, ran for 1 year, and then we said that in that case we'll be able to make a distinction between cosmological and astrophysical origin, provided we'll be able to get rid of the loud astrophysical foreground, which particularly the BNS population, as it has been shown in a paper like a year back, it's going to limit the sensitivity of 3G detectors. But this is a work in progress, which is important. Now, the last thing I would like very briefly to comment is up to now, I discussed about the isotropic background, but the same way, like for the cosmic microwave background, here we're going to have anisotropies. Why we have anisotropies? Because there is an anisotropic distribution of the sources, which are going to lead to the stochastic background. And then I can have an independent way in order to map the large-scale structure of the universe. Okay, so in the CMB, you take the correlation between the temperature fluctuation in 2 points. Here we'll have the fluctuation in the omega star. And about a year, I don't know anymore, 3 years back, we had set up a formalism in order to do that, which is exactly the corresponding formalism that people are using in the case of the cosmic microwave background. So here, for instance, you see from the last observing run the maps of the anisotropic distribution for the case of alpha equal to 0, the frequency dependence 2/3 or equal to 3. Okay, and which came from the LIGO Virgo Kagra collaboration. Now, what I'm going to discuss here is I will go to make a comparison between what the data tell us and what, from a theoretical point of view, we can do. We make this spherical harmonic decomposition, which is something that usually we use in order to be able to find large regions in the sky with a rather smooth frequency dependence. There is an obstacle which we have, which is the diffraction limited angular resolution of the sky, which give us what is how good the resolution can be. And unfortunately, it cannot be extremely good because it's going to depend on the distance between the detectors and the frequency at which they have better sensitivity. And it goes inversely proportional to that. So the multiple moment L, which goes like 1/θ, cannot be very big. As we can see, for instance, for 2/3, which is the CBCs, it cannot be bigger than 4. Okay, so here are the data that we got from the last law 3 of the LIGO Virgo Kagra collaboration. And here is what theoretically we were able to do by just taking maps of the sky where we know where galaxies are, where we can trace back where compact binary coalescence took place. And here is, I believe, a nice a map of the sky, which is the corresponding one of what people do with the CMB we did with gravitational waves. The same way, we were able to to compare, in the case of cosmic strings, what is going to be the constraint on the monopoly here that you can see, and what is the constraint that we can put from the theoretical studies that we have done. As you can see, in both cases, we gain about, theoretically, we're better about 3 orders of magnitude. What I would like to emphasize here is whereas what is the model of binary black holes for their mass distribution and speed, and what is the model of cosmic string is going to put a footprint in the isotropic omega GW. This is not the case for the anisotropics. What is the mass distribution of my binary black holes? What is the model that I take for my cosmic strings? We have checked, and this does not really play a lot of importance. That is what I try to write here. Now, I would like also to make a comment that so far we have discussed only the anisotropies which come from the anisotropic distribution of the source that leads to the gravitational waves. But there are going to be more kind of effects because they move through an anisotropic distribution. And we have already a theoretical study of that, and I believe within at least a couple of weeks we'll put in the archives a big study where we took into account all these effects, analyzing with the most current data that we have from the collaboration. So let me then go to my conclusions. A detection of gravitational wave from unresolved compact binary coalescence is expected to be made by Advanced LIGO, Advanced Virgo at their design sensitivities. Of course, if we can do it before that, that would be great. So I tried to highlight that we have the methodology that can allow us to detect a gravitational wave background in the presence of correlated magnetic noise. So once we have a detection, we know that is a real one. It seems to be that it is difficult with the current network of detection we have to make a simultaneous estimation of astrophysical and cosmological background, but with 3 detectors we'll be able to do it. And I highlighted how a detection or even or not detection can put constraints on models that come from beyond the standard model particle physics, about models of the universe, and as well about astrophysical models, compact binaries, the possibility of existence population 3-star, and so on. And of course, let me finish by saying that isotropic and directional searches are an ongoing effort of the LIGO, Virgo, and Kaggle collaboration. Thank you very much.
Sure. Thank you very much. So I could not imagine a more complete review of the subject that we just heard. If I may use I have one comment and 2 questions. One comment is in gravitation, at the moon, most probably the astrophysical background goes down quite low. Probably it will be less problem than it is on the Earth. Isn't that true? I mean, it's going, you see it's up to the two-thirds, I don't remember. It's going down, so it's probably better.
I believe so. Yeah, I think I agree with you. I mean, this would be much better. Yeah.
Well, that's the one thing. The second, if you correlate something at the moon with a terrestrial detector, then you unfortunately do it on different frequencies. This puts ambiguities in your analysis because you have most of them have some kind of spectral form. Then is it? Can you do that between the Earth? You have to use the same frequencies.
You have to use that frequencies. I'm not sure how this could be done, to tell you the truth. But also, I've not thought about that. But at least the methodology that we have used, it will have to be modified. It cannot immediately.
Some kind of extrapolation somehow, some link between the frequencies, because otherwise it's 2 different frequencies. You cannot use it.
But it's an interesting question to be able to do that. But I don't know how.
How you would do it. And the third is also to our geoscientist friend. We also have a magnetic fields in the moon. On the moon, eh? Can we have a Schumann effect in the moon? I don't know. No, not really. It must be less important than.
I think it's less important. I mean, we just finished another study about how this is going to be important for the Einstein telescope, and what the choice of this transfer function should be. But I think that is not. I mean, it's not going to be a problem for the moon.
I see. Okay, my questions are over. Anybody else?
maybe just to the discussions that you started, maybe 2 comments. So first of all, okay, Schumann resonance, of course, is a real terrestrial effect as it requires the atmosphere. So, you know, but for the correlation, I think it's in principle interesting, the correlation at low frequencies between different planets, if you want, starting Moon, Earth in principle. The overlap reduction function is fine for these low frequencies between Moon and Earth, you know, below Hertz, because it's like a second of light travel time. So you can, you know, you can estimate from that where the overlap reduction function would start to drop. So it can in principle be done. In fact, we have used Apollo seismometers and terrestrial seismometers to correlate their data and search for stochastic backgrounds. Of course, there the limitation comes from the fact that Earth is way too noisy. Now it's a futuristic scenario, but I guess in principle, if you make deployments, let's say, I don't even know, I don't want to speculate too much, but I mean, you know, if you had 2 quiet places, two bodies to deploy seismometers where it's really quiet, then of course, in principle, you can make these games. I mean, but you can, by the way, you can even start to do that on the Moon, right? So if you have, let's say, deployments on the North Pole and the South Pole of the Moon, then the overlap reduction function between these 2 deployments can be very large if the seismometers are oriented in the same way. So between these 2, you can actually get, even for stochastic signals, maximal correlation essentially. So you don't necessarily need another celestial body to make your correlation measurements. Yeah.
If I can jump to something that, I mean, this question and the discussion is something that interests me as well. So if people would like to catch up on I mean, afterwards or whatever by email, I would be interested.
Okay.
Do I understand correctly? On the Moon, you're using the whole Moon as a vibrator, so it is something that oscillates as an oscillator. So the correlations are built in by the motion of the Moon. They are not part of the directionality of the gravitational wave. So I'm not sure that this will be so. You have to factor in. It's very different. The analysis will be very different from the analysis of 3 detectors on Earth, which each one of them is completely independent. Because you have to, in the analysis, you have to factor in the normal modes of the Moon. So it's a different story.
So I mean, no, I mean it depends. It depends. It depends because there is no. You're not thinking. I mean, at high frequencies, you don't need to think about known modes anymore. It's not a global excitation. So you really. So you have all the signal will, you know, if you have 2 seismometers located at the same position, but with 2 orthogonal measurement axes, they can measure uncorrelated signals in principle. So uncorrelated gravitational wave signals in principle. Of course, for the normal mode frequencies, that's not true, because a normal mode would coherently excite all kinds of directional displacements, but that is for the higher frequencies, there is the randomness also in the signal, in the displacement. Well, no, they're local. I mean, what we heard today from Raphael, essentially, he talked about amplification factors, which are really connected to nearer surface geologies. Ah, okay. Yeah, it's not a normal mode anymore. No, we're talking about amplification factors that that you might potentially also call side effects, but I mean, I still, it depends on frequency. I agree when you look at the normal modes, correlation measurements are, it's not even necessary because a normal mode is just a coherent global mode, and there's no randomness in it. Thank you. It was really great talk.
Thank you very much. Thank you.
Oh, sure. Yeah, you're where right now, Mary? You're Los Angeles or somewhere? So it's good morning or something? No.
Good morning. No, I was at UCLA. Right now I'm at Caltech because I'm supposed to give.
Caltech. Okay. So thank you very much. Thank you very much again. And
I wish I was there. Thank you very much for the invitation. Thank you.
thank you. So it was a long day. Thank you very much. So you're invited for the dinner. I hope you understand where it is. It's in San Martino. It's a very central road. If I hope there is, for the hotel, it's very close. It's, you just go from the hotel, you go up, and in the first road, you turn to the right and you find San Martino and you walk on it, and it's 6 minutes, 10 minutes most. Okay, if anybody wants